chat box. Well, yeah, thanks, Marco, again for invitation, and yeah, thanks for coming back. I guess it's sort of early morning here, but not so much there. So I guess it's maybe not too inconvenient for you guys, but well, good morning, afternoon, wherever you are. So I wanted to continue with a presentation from yesterday, but just real quick, I wanted to, just in case you missed it here. So you can find my website is here. I sent the link to the slides. That's also through my website, so you can find both the slides are there, and any of the references that I'm going to talk about during the presentation today, you can find on the website there. Let's see, so let's jump to start for today. So yesterday we completed part one, so today I want to start part two. So part two, I expect will go past our mid-session kind of break. So I'm expecting maybe this will fill up the first part of today, so the first like hour and a half roughly, and then maybe part of the second, and then the part three will be relatively short. So I think we can finish all this in the time allotted. So what in part one, what I tried to do is to convince you that if we're interested in doing probabilistic inference, which means doing some kind of uncertainty quantification about unknowns based on data, and if I want that to be valid in the sense that those I'll call them probabilities that are returned by this output, that those are reliable or valid in this specific sense, then we need to go to imprecise probability. That's the only way to go. So I showed you something there, which was to take some kind of p-value or some kind of confidence region and to use that to do this, kind of convert those familiar things into a valid inferential model. But it turns out that's not the only way that you can do it. So you can actually construct these things directly. So that's what I want to talk about today, is that general construction. And then there's kind of this follow-up question. Well, basically it's easy to achieve validity. The question then is, how do we fine-tune that so that the results are both valid and efficient? So I must have it somewhere, but most of what I want to talk about today is contained in the book that I mentioned last time. So I'll have some references here, but no more pictures of the book, no more commercials. Okay, so here's the outline for today. I want to talk about this basic kind of direct construction, how this leads to that validity property. I'll show you a few examples, relatively simple ones to start out. Then that will lead to this question about sort of what's the next thing beyond this validity, and that's in order to achieve some kind of efficiency. And the way that, I guess, as far as I know, I think the best strategy or best general strategy for achieving efficiency is to employ certain kind of dimension reduction strategies. So this will have something to do with looking at some kind of conditioning or doing some kind of marginalization if the problem allows. So there's a few things that kind of go beyond this kind of basic setup, and I'll just make a few brief comments about this. There's a thing which I've called a generalized IM, and I'll explain what I mean by that. But then there's an interesting problem that's different from the one that we've been focusing on, which is statistical inference about this prediction problem. So this one is interesting because it's kind of an extreme case of marginalization where, in fact, none of the model parameters are of interest. You sort of want to marginalize out all of those model parameters to get directly to something about maybe the next observation so you can do the prediction. Okay, and then I'll end with this part two, going back to that characterization theorem that we ended with last time. I remember I left off some kind of details because we didn't have all of the notation and stuff, so I'll kind of fill in that what was missing in that characterization theorem. Basically, it's that how we carry out this construction. Actually, that characterization says that the valid IM that corresponds to any given frequentist procedure that has good properties corresponds to the structure that I'm going to describe here. So that's the part that was missing, and I'll fill that in at the end of this part two today. Okay, so I want to start just as a reminder, since we've had a few hours of break, maybe forgot. So the problem setup is like this, is that, so I'm in a statistical context, so I have data that I can observe. There's some model which I'm going to specify, and this model will connect the data to this phenomenon that we're trying to investigate. And so the way this works is that there's kind of a collection of these probability distributions indexed by some parameter space big theta. And then the idea is that I don't know which of the thetas is the real one. So I have these generic values of theta, I'll write with this kind of different theta font, and this regular theta font is for that value that I'd like to learn. And so the goal is to quantify uncertainty about that unknown once I get to see this data. So data will come, and then I want to take that data and I want to learn something. I don't quantify my uncertainty about that unknown theta. So the way I want to quantify this uncertainty is with this thing I'm calling the inferential model. And so inferential model is just it's a mapping that takes the data and returns this, what I'm calling here a data dependent capacity. It's just some kind of lower probability that takes assertions in the parameter space, the space where the unknown lives, and then attaches to those things some degree of belief. Okay, so we talked a bit about this last time. And so that's the thing I want to use as a uncertainty quantification. And spent some time in the previous part talking about what does it mean for this inferential model to be reliable or sort of quote valid. And what was kind of the main message coming out of the part one was that if we want to achieve validity, then we can't be additive, that this sort of necessarily requires that we consider some kind of imprecise probability. And that's why I'm using this lower bar type of notation that says we are actually going to be talking about imprecise probabilities here. So the main question for part two is how do we actually construct this thing? So last time I was describing something using p-values and stuff, and that was kind of indirect because we first we already needed some kind of solution to the problem, and then we could kind of add on to that this imprecision and the corresponding validity property. But that's not really the way this kind of this work began. It was sort of how do we sort of directly get to something that can achieve this validity property, and then later we realized that of course it needs to, in order to achieve validity, it has to be non-additive or some kind of imprecise probability, not exactly the path that I described to you last time. Okay, so here is the way we originally approached the problem, was that the basic, model formulation says I have data Y and it's distributed according to this distribution P of, here this is like Y that's indexed by theta. So this means that there's some distribution that depends on some unknown theta that corresponds to the Y that I can observe. And so what I want to do is I want to take that and I want to give that a little bit more concrete sort of form. And so I'm going to write this as what we call an association. And this is an association between data, unknown parameter, and some unobservable auxiliary variable. This might look familiar in the sense that this is how you might generate data from such a distribution, is that this A is some function that's known. And so what I would do is I would generate some kind of random seed from a known distribution, plug it into some formula, maybe like an inverse CDF type of transformation, and then the results would give you some Y, and that Y is known to have a distribution like this one. So we could think of this as basically as an algorithm for how you might simulate data from this model. But I want to turn this around and actually to say I want to use this this type of representation to provide some kind of insight and to help with inference. So it's true that there is not a unique form for this, and that kind of gets us to that question we'll deal with later, is that I want to reduce the dimension as much as possible. So I guess my response to the non-uniqueness would be that if you can find two representations like this where the U is the same dimension in both cases, that these are effectively equivalent. If you try to match up things that are different dimensional U, it's better to have the lower dimensional one, and I'll explain that later. But this question about non-uniqueness of this representation is one that maybe deserves some discussion. So what is this intuition that comes out of this representation? Is that so if I'm expressing my data as being generated according to such a form. So now if it happened that I could see what that value of U is, if it were that U were observable, then I would see Y, I would see U, and then I can just solve this equation. So then there's nothing really to do. It's just a math problem, solve that equation, and then I've solved the inference problem. Okay, so the real obstacle is that U variable is not observable. What saves us is that we actually know something about this. So this U is in this representation, the U comes from this known distribution P sub U. So because I know its distribution, I can figure out a way to do a good job of guessing what that unobserved value was. So it's that unobserved value of this u that I want to know, because if I knew it, I could solve the equation. So using something about this piece of u distribution to try to guess at that unobserved value, that's sort of the key here. Okay, so I'm kind of more writing this a bit more formally so that we can imagine going step by step. So this A step is for association. And so what I want to do here is I want to write that expression y equals a theta u. And then I want to convert this into something which is basically a set valued mapping on a parameter space. So what this would do is take pairs y and u and map into sets of theta that are consistent with that pair y and u. So consistent in the sense that you could imagine that there is a parameter such that that u would correspond to the observed y. Okay. So here's kind of the intuition. So suppose that if I observe y, and then I happen to know that u is equal to u, then I know for sure that the true value of theta is in that set. Okay. And this is the strongest that we could, the best type possible answer we could ever give. So generally, or not generally, but in many cases, this set is a singleton. So you could actually solve precisely for that value of theta, and then you'd be done. Okay. But this is make-believe, because we're talking about some kind of an oracle was able to whisper some secret to me into my ear. That's not real life. So what we need to be able to do is to harness some kind of information that's contained in that piece of u distribution to come up with good ways to guess or quote predict this unobserved value of u. We can't rely on the oracle to tell us. Okay, so that's the goal. Is somehow I want to guess or predict at this unobserved value of u. And so how can we go about doing this? So if what we were trying to do was to characterize uncertainty about a new sample taken from this piece of u distribution, then naturally the way we would quantify that uncertainty would be using piece of u. Okay, but what we're trying to do is different. So the unobserved value of u has a different status. It's a different type of unknown. It's a fixed thing that's unknown. So it doesn't really make sense to think of this piece of u as like the sort of this posterior type of representation of uncertainty. That's not the right way to think about it. So what we want to do is we want to acknowledge this status change from going from thinking about a new sample from piece of u to a unobserved value that was drawn from this piece of u. And so now we're thinking about what I want to do is this status change sort of suggests that we think about some kind of imprecise probability that's to try to quantify that uncertainty in a reliable type of way. So this second step of the construction, and I'll have some more things to say about this, is to use a random set to do that guess or prediction of the unobserved value. So I'm going to use this kind of calligraphic font S, and then I'm going to say this P sub S is its distribution. So it's random sets have distributions. So like Ignacio talked yesterday about random sets having some distribution. Here, I'm not necessarily thinking about a discrete type of like sample space. So these are sort of more general type of distributions of random sets, but we're able to handle this. These random sets don't need to be so complicated. So we're able to handle this computationally, even though it's uncountable spaces. So just as a sort of preview, there's maybe another way, or there is another way to describe this sort of directly using possibility measures as opposed to thinking first about random sets. They're not exactly equivalent, but I can say a few words about this at the end of this section. All right, so the two steps we've done, association was to kind of connect this data unknown to this unobservable auxiliary variable, the u. And then the P step, that's the second step. This one is about prediction of that unobservable value using the random set. Okay, so we kind of have we now have two sets. One is on the U space. That's this calligraphic S, right? That's defined on this U space. Then we have this other set, the theta y of u, which is set on the parameter space. And so what I want to do is I want to combine these things, or sort of push this uncertainty about the unobservable value of the auxiliary variable to the parameter space through this association mapping. And this push forward goes in this way, is that I will look at all of those sets of theta which are consistent with a pair y and u, and then a union operation over all of those u that are inside of this that draw from random set, or the random set distribution. So I'm going to call this one, it's like the same notation here, but I'm going to plug in, instead of a u, I'm going to plug in that set of u's. So this is kind of like the image of the random set S when you apply this theta y mapping. Okay. So then what we say here is the output of this inferential model is, in fact, it's the distribution of this random set with respect to this piece of S. So it's just a kind of a push forward mapping of this specified piece of S distribution to the parameter space through this theta y mapping. Okay. So it's just, we had a random set on the U space. Now we have a corresponding random set on the theta space. And once we have this corresponding random set on theta space, now we can do various kind of calculations, very much like what Ignacio described yesterday. So I can use that random set to calculate beliefs or lower probabilities. I can use the random set to calculate plausibilities or upper probabilities. And the formulas are they're the same as what Ignacio is describing. So this one would just look at this belief or lower probability, looks for outcomes that imply the assertion A. Right, so this is like realizations of the random set that are completely contained inside of that assertion, and so that's counted as sort of evidence in support of that, in support of the truthfulness of that assertion. And so this probability we call the lower bar pi. That's my belief or my lower probability. And then I can, from this one, I can directly calculate the upper probability or plausibility using that kind of a conjugate form. But there's a direct formula for it. You just look at any instance of this random set that's not inconsistent with A. So if you look for their intersection to be non-empty, that means there's some kind of consistency between those two things, this set and this set. And so we just accumulate all of the mass assigned to such events, and that would be my plausibility or upper probability. There's another quantity that will actually turn out to be important. It's maybe not immediately clear why this is particularly important, but we'll see. This thing I'm going to call the plausibility contour. And so this is just a simple function that takes point arguments and returns a plausibility value. This one just looks to see if the set contains this generic theta value. So this is good for drawing plots, right? So drawing plots of the belief and plausibility as functions of assertions is complicated because you can't, this is sort of too high dimensional to actually visualize. But often if this elusive parameter is relatively low dimensions, this is a nice kind of visual summary that we can present. It sort of describes what does the data say about this unknown parameter. Okay, so what's special about this is actually the introduction of that random set at the start. So that's what makes this particular construction unique. Much of what's going on here is contained in what Fisher had originally described back in the 1920s and 30s, and then also in Dempster's extension that was sort of originated in the 60s. A way that you could understand Dempster's approach within this framework is if you took that random set to actually just be a singleton. And so this then amounts to basically what I said was kind of the way you would treat this if what you were trying to do was to predict a new value of U from its distribution. So you might just take that prior distribution as the corresponding posterior and just go like that. So that's the way Dempster had described to do it, at least a way that you can think about Dempster's proposal in the framework that I just described. So the problem is that we have to be careful about the choice of this random set S if we want to achieve validity. And so it turns out that if you take this form according to what Dempster's procedure would be, so just using random singletons, this will not achieve the validity property. So if we need to, if we're insisting on achieving this validity property, then we need to consider non-singleton random sets. Okay. So Marco is, okay, Marco, I don't know if it matters, but the thing you sent me is a private message. I don't know if you meant to do that.
I didn't mean that.
Yeah, so you're just asking here about, I guess that maybe Russians use random set while French use belief functions. I guess I don't know if that's true, but I guess maybe it is.
Yeah,
I think that's consistent with my experience too. I don't know if it's true,
sorry,
but
it's not. It was not. It's not to you.
Okay, never mind. Okay, so so when we switch from thinking about singleton random sets to non-singleton random sets, what's kind of the effect of this? Well, when we introduce the non-singleton random sets, that'll create this gap between the lower and the upper probabilities. And so this actually is important. So that gap is what corresponds to non-additivity. And so if we need non-additivity to be valid, then we need this kind of gap between them. So these singleton random sets just generally will not work. And you can even kind of see what's going on here is that, you know, it's if we made this random set really big in some probabilistic sense, then the gap would be really large. And so then it's maybe possible to achieve validity relatively easily, but this you'll be giving up in terms of a certain kind of efficiency. What we need to do is basically to balance. We need this thing to be a non-singleton set, but not too big, right? That's basically the idea. Okay, so this is the, you know, what we were trying to do. I mean, the whole point of this was to go through some kind of a inferential model construction such that the that validity property can be satisfied. So just a reminder of kind of what this validity property means. We're talking about, you know, it's a bad thing if we happen to be assigning large degrees of belief to assertions that happen to be false. So that's something that we would like to avoid. And so what this validity condition is designed to do is to prevent that from happening. So this is related to sort of the reliability of those belief assignments from, you know, one application to another. So here's that definition. This is some kind of a summary of what I presented yesterday. So this first line is the version that I just described about, here's a case where theta is not an A, so that corresponds to a false assertion. And this would be an event where false assertion is assigning relatively high, or sorry, lower probability is assigning relatively high belief to a false assertion. And so validity says, I want to try to make that to be a rare event. So that's what's going on here in this first line. It says false assertions won't tend to be assigned high belief. And because this holds for every assertion, I can flip it around using that the conjugacy formula and say a similar kind of property for the plausibility assigned to correct or true assertions. And so I shouldn't be assigning small plausibility to true assertions. Same deal here. So they're equivalent because I'm requiring this one for all A and this one for all A. So here's what the validity theorem for this IM construction I just presented says. This is not really a helpful statement, but at least it gets to the point, is that if we make a suitable choice of that random set, then validity is satisfied. So that's I mean, really was the whole point of this, was that I turn the problem into one about how do I predict the unobserved value of U, and if I do a good job at that, then I must do a good job at the inference problem. That's how it works. So just a reminder of like what are some of the consequences of achieving this validity. It's that, well, we can immediately construct tests that will control the type 1 error. We can immediately construct these kind of I call them here plausibility regions, and that those sets are actually corresponding. They achieve this desired coverage probability. So the advertised coverage probability. So many of the things that statisticians are interested in achieving, these are consequences of the validity property. So that's one of the reasons why we would like to be able to achieve this. So then there's this question. I mean, I left it super vague sort of intentionally here because there's some discussion that we have to make. But obviously this comes down to what does this mean, right? Suitable choice of this random set S. So let's try to get some intuition about what's going on. So what I want that random set to do, right? So let's back up a bit. So if I imagine that unobserved value. So I don't ever get to see it, but technically it's a function of the data that I can see and the parameter that I don't know, right? So that's what this thing would look like. And so if we go back through that kind of how we define that new random set on the parameter space, there's this kind of implication here that's really critical to all of this, is that the true parameter is inside of that realization of the random set, if that realization of the random set contains that unobserved value, or if and only if, right? So it's like these two things are equivalent. So this is why we can convert this problem about thinking about inference about this unknown parameter completely can be converted into something that's related to that auxiliary variable, right? And so before seeing the data, that thing that I'm interested in trying to hit with my, that target for my random set, it itself is a realization from this U distribution that I know. So the point of this is, well, if I can choose this S, random set S, to be good, sort of quote, I still haven't explained what I mean by that, to be good at predicting realizations from this known distribution P of U, then, for example, that plausibility contour at the true value, it can't be, or it's at least unlikely to be small. Okay, so it's because of this implication. So if I'm good at hitting this target, then I'll be good at hitting this target. And hitting this target means that this plausibility contour would be relatively large. Okay, so this is entirely now in my control, because I just have to decide, or I have to figure out how to choose this random set S to be good at predicting realizations from this P of U distribution. But all of this is in my control. I know P of U. I can choose this random set however I like. So that's, I think, is unlike in the kind of so I guess as an analogy, you can kind of think about what would make a Bayesian solution sort of quote good. Well, you have to have a prior distribution that somehow is good, and being good, prior distribution being good basically requires that you know something about this unknown parameter. And in some cases you do have that information, in other cases you don't. Here, this is completely under our control, is that P of U is something that I've chosen, I know it. The S is up to me to decide. So this is completely separate from any unknown, unavailable information about parameters and so forth. All right, so get a bit closer to what does it mean for this S to be good at predicting realizations from this P of U distribution. Here I'm using another, it's valid as being used again. I think it's okay to use the same word to describe two properties, because they're essentially the same property, just in a particular context. So what does this thing say? It says, so take that random set S distribution P sub S, and let's define some function. So this is just a real valued function, or takes values between 0 and 1. This is a function on that U space. So I'll write it here as F. I think in papers and books, sometimes I use gamma. But anyways, here is F. And so this function is just what's the probability that that random set covers this particular U value. Okay. So this is a function that you can compute once you know this P of S distribution, you can compute this kind of function. So it's normally I'll show you this random set is relatively simple in its form. So this computation is relatively easy. So the thing that we need to be satisfied, this kind of condition that what makes it to be a suitable choice of S, is that it has this property that if I were to draw U from P of U distribution, then that random variable F of random U, that it's stochastically no smaller than uniform. A way you can think of this is just that it is uniform. Stochastically no smaller is obviously more general, but think of this as just saying that this F of U random variable has to have a uniform distribution. Okay, so what this does, sort of mathematically, this sort of forges some kind of a connection between that P of S distribution and the P of U distribution. Somehow that was obvious that it was needed, but this makes that more precise, because remember the intuition was that S needs to be good at predicting realizations from this one. So there's definitely has to be some connection between these two distributions. I can't just sort of arbitrarily choose my P of S distribution. It needs to depend on the P of U somehow. So here is a way in which it needs to depend. So a couple of extreme cases, maybe to get some kind of intuition here. One is that, what if I just gave up on trying to do a good job and I just said, let's just always take the random set to be equal to the full U space. So if you kind of think about what would happen then, so if I chose it this way, then obviously this f of u would just be equal to 1 for every u. Right, and so then if the f of u is equal to 1, no matter what u is, obviously this, if I plug in a random u, it's still equal to 1. And so then this would be bigger, much bigger than uniform. So it's definitely would be stochastically no smaller. The other side is if I took the singleton random set. So now this, assuming we're in this kind of a continuous type of a domain, this would be like a single point covering another single point, right? So then in this continuous domain, obviously then the f of u would be equal to 0 no matter what the s is, okay? And so then this would fail because f of u would be equal to 0 even if it's a random u. So then it would be stochastically smaller than the uniform, and so then this validity condition here fails. Okay, so these are the two extreme cases. Obviously, neither one of those are really interesting. It's about trying to achieve this one in kind of a non-trivial way or in an efficient way. So I forgot to say at the beginning, but obviously you're welcome to yell out if you have questions or type something into the chat. I guess otherwise I'll probably just keep going. So so if you want to stop and ask some question or something, please feel free to interrupt, either yelling out or on chat. Okay, so this is still again talking about how do we make this choice of the suitable choice of that random set. So we have that definition above, which was about what does it mean for this random set to somehow be kind of correctly connected to that P of U distribution. But here, when it gets sort of more directly, it's some kind of like a sufficient condition to be able to achieve that property. So let's just take some generic H function. So it's a function that goes from the U space to reals. And so it has to be in such, I mean, this is kind of technical, but basically I can't have this H function to be sort of constant on sets with a positive measure. So, because that would create some kind of atoms in this distribution of H of U. So basically you can think about this H as just being a smooth function that's never constant. A good example would be like one that's sort of one of the favorites in some sense is like this. This is a function which is nowhere constant, so it's never runs into this trouble about not being non-atomic or being atomic. So then if I take this, I use this just an ordinary function H, and I define a random set using that. So this is just a kind of random level sets of that H function. So here's, just to be a little bit more precise, is that I'm imagining, so P of U is this distribution I know, and I imagine that I can take draws from this distribution. So then I can take draws from the S distribution just by collecting all of those U's such that the H of little u is smaller than this random variable H of U. So that makes the S a random set, and it's obviously connected to that P of U distribution. And this one satisfies this type of property here. In fact, it achieves it with equality, that this one is exactly distributed as uniform. And it's easy to see. This is basically, you convert it into the CDF of a random variable H of U, and then the CDF of H of U. Right, so it's like the CDF evaluated at the, right, I maybe said something about this. It's hard to say in words, so let me just jot it down real quick. I should have put it on the slides, but I forgot. Okay, so there's this basic property, so that it says if X right? Assuming everybody's continuous and all of that, right? So if I'm dealing with a continuous random variable has this strictly non-decreasing or strictly increasing CDF, then there's this property. So this is a basic property from first probability course. And so that's what's going on here in this here in this case. It's that what we're ultimately, when we look at that coverage type of function, this is just the CDF evaluated at the random variable whose CDF it is, and so then you inherit this kind of a uniform property, and that's the how you check this. So one example that we'll use here in a second is one that we've called in some papers, maybe also in the book, sort of quote default choice, and so. This one makes sense when you're talking about situations where that P of U distribution already is a uniform distribution. And so if what you're trying to do is to do a good job of predicting a realization from uniform distribution, then choosing this H in this way it's a reasonable choice, at least. It's maybe not the best, but it's a reasonable choice. So this just amounts to, if you take this H and you plug it into this expression here at the top, what it amounts to is you just, it's a random interval centered around half. So it's a random interval inside of 0, 1 interval, and it's centered at half, and its width is random. Right. So what we'll see, I'll have some explanation of why this is the case, but I won't say too much about it, is that this H, can think of it, it actually needs to be sort of bowl-shaped in the sense that when we do this kind of level set construction, that will create some kind of nested sets. So Ignacio talked yesterday about nested sets, and so that the nested sets actually turn out to be important in this context. That basically it's that I can never do, what is it? That the in terms of efficiency, nested sets are all we need to consider. So basically that there's no reason to ever consider these kind of sets that are not nested. And therefore, the way we want to think about this H function is some kind of a bowl-shaped function that will force this these sets to be nested. So here's the example. So first one is maybe one of the simplest ones, although this is also kind of messy, but for a binomial distribution. So here's the case where y is some integer 0 to 1, and then its distribution is binomial. It has a success probability that's this theta, and that's the thing I don't know. I'm going to use this notation. The f of theta is the CDF for this binomial. So a way that you can make this association, so one of the reasons I wanted to show this was that the association, I wrote it before as like a y equals a function of theta and u. It doesn't actually have to be like an equality. So it just has to be some kind of a recipe for how you can simulate y from that distribution using some random seed u. And so here is a way that you can do that in the binomial case that's not really like an equation, but this is still a valid type of an association. So now you see, okay, here's this thing, and I didn't write it, but it does basically collect, there's this idea of collecting different theta values that would satisfy this kind of sequence of inequalities. So I guess it is right here, is that this would be all of those theta. So for a given y and a given u, all the theta that satisfy this inequality. So here I'm using that sort of default random set that I just described. So it's a uniform auxiliary variable. So I can take this random set to be this random interval centered around half. And now if I push this random set S through to a new random set on the theta space, the operation is like this one, and it turns kind of messy. But anyways, it's a thing that you can calculate. This G now is like a beta distribution CDF, and there's some connection between binomial and beta. So yeah, Dominic has a question about this Klopper-Pearson. So this construction, no, but there are other ways to get it. I'll mention something about that a little bit later. So this construction directly will not give the Clopper-Pearson, but there is a choice of this random set that will give you that. So I'm just showing you one that's simple. You need a more complicated kind of random set to reproduce the Clopper-Pearson intervals. So the main idea here, I guess, from this construction is just that, and because things are relatively simple, you can get down to this final expression and you see this just depends on a random variable here, u. So now if I wanted to calculate, for example, what is the that point plausibility function. So that would be something like the probability that this random set contains a particular value of theta. What I would have to do is just look at, I would just need to be able to calculate probabilities with respect to the u distribution, and u is just uniform. So like, for example, if I wanted to know whether this interval contains the theta, right, some generic value of theta, I can just check whether the lower endpoint is smaller than theta and the upper endpoint is bigger than theta. And those would be functions of u. And then they define events in terms of the u random variable, and I just calculate probabilities with respect to that. So I don't actually ever have to deal, at least in this case, directly deal with computing probabilities with respect to a random set distribution. It's all boils down to just random variable computations. In this case, it's uniform, so I can actually do it closed form. But in other cases, I may not be able to get like closed form expressions, but I can simulate and do Monte Carlo approximations for some of these probabilities. So that's I guess the main point at the end here is not what this formula looks like, but that it only depends on this random variable, not a random set. So here's a couple of pictures to kind of help to visualize what comes out of this construction. So on the left, well, I guess the setup is I took 18 observations and there were 7 successes. So then, we expect that there's would be strong support for theta being equal to 7 divided by 18. So what is that? Something around 0.4. So if we were looking at this plausibility contour, which is kind of like that's the probability that the random set on the theta space contains this generic value, right? So what would be good is if there's kind of strong support for what we know should be a good guess of that parameter. So something around 0.4 would be a good guess, 7 divided by 18. And so here what we see is that as if you're plugging in those theta values, which are sort of towards the endpoints, right, that plausibility is relatively small. But as you get closer to this sort of place where we would expect the action to be, plausibility function is increasing. There's this flat part at the top. This is a result of the discreteness of the problem. So there's sort of inability to distinguish certain ranges of the theta values as being sort of the best based on this particular construction. But anyways, we see that it's kind of peaking around where we would expect. So this is a nice kind of visual summary, I think, of what the data has to say about the value of theta. So in some way, this is kind of like, if you familiar with some Bayesian calculations, they may draw plots of like the posterior density, and you use that to somehow think, okay, this tells me sort of roughly where the data says that unknown parameter ought to be. What's difficult about Bayesian posterior, which is not so difficult, which is easier here, is that if you're dealing with this Bayesian posterior distribution, the operations you have to do to kind of summarize that are integration. Right? And integration isn't something you can really do in your head, right? You have to somehow be careful about the scale of the problem and things, the scale of these things and how big the dimension, whatever. But here, remember from last time we were talking, is that this ultimately turns out to have something connected to these possibility measures. And so the relevant type of operations that we do here are optimization. And so if you remember, there was a formula about, okay, how can we extract some kind of say a plausibility interval based on this kind of output. And so the thing that we would do is we'd define some threshold, maybe 0.05 or 0.1. That's like that alpha value we were talking. And I would draw some kind of a horizontal line here at that alpha value. And then I just have to collect all of those theta values whose point plausibility function exceeds that threshold. So I can easily do that just by looking at this picture. I don't even really need that line. I can sort of visualize, okay, if I had something around 0.05 here, looks like it hits around 0.2 and maybe over here around 0.6. So just by looking at this plot, I can see that roughly maybe a 95% plausibility interval would be about 0.2 to 0.6. based on this problem, I don't need to do any integration of this function to extract that kind of information. What's on the right side here, I mean, this is maybe a little bit weird, but what I'm doing here is looking at sort of sequences of assertions indexed by this theta value. And so as you increase the theta value, the assertion gets wider and wider. And so what I'm showing here are the lower and upper probabilities attached to those sequence of assertions. And so as I didn't have to distinguish the lines, it's clear. So the one that's to the left, that's the upper probability, and the one on the right is the lower. So these are both basically, they're both CDFs, but there's this gap in between them, and the gap is controlled by that choice of the random set. So as if you had more data, you would see this kind of gap between them start to close up. Yeah. So I guess also related to Dominic's question, that the kind of contours you would see, well, okay, maybe, okay, I guess I have to think now. I don't think that this is exactly the Klopper-Pearson, but maybe it is. I could be, now I'm second guessing myself. Right, because in order to improve on Klopper-Pearson, you have to, this function starts having some discontinuities, sort of jumps and stuff. So yeah, I guess, okay, but let me back up. So I think that this is very much like the Klopper-Pearson solution. Ignacio has a question here. So this is about the P box. So I think so here you're talking about, yeah, so this is the P box, I guess I don't really think about in that term, but yeah, so this does correspond to the P box associated with this plausibility measure like that, yeah. Okay, so I guess the second set of examples here, in some way this is actually simpler than the one that we just did. But I'm doing it in kind of a general way to cover several different cases at the same time. So the examples that Fisher originally considered when he was developing his fiducial inference were these kind of problems where everything's a scalar, and so you have continuous type of CDF for the theta. So it's continuous in both both y and theta, and that there's a sort of a funny, sort of maybe unexpected kind of condition is about, it's sort of unconstrained, that for fixed y, as you vary theta over the space, this f theta y goes from 0 to 1. And similarly, if you fix theta and you vary y, then you go from 0 to 1. So that's the definition of CDF, but you have to go the other direction too, is that if you fix y and you vary theta, that you can get anywhere in 0, 1. Most problems satisfy this, but not all. So what we can do here is write that association actually in the way that we had considered this I gave as kind of the basic example for this, was use an inverse CDF type of transformation with a uniform U. So here I'm doing that specifically. And if I stick with that kind of a default type of random set using the interval centered around, random interval centered around half, then this takes a relatively simple form now. So that's this random set like here. And so then if I wanted to calculate, for example, like that point plausibility function, it's looking at this random set containing that some generic theta value. And then you can undo this thing and make it look like just a probabilities based on a uniform distribution. And here's what the result is. So this is a fairly direct and general just strategy. So you can immediately write down this formula. It just involves that CDF that was assumed. And so I can easily and very quickly calculate this thing for really lots of distributions, all in sort of one stroke. It seems as if this is sort of too simple of a problem to be ever really relevant. There is that I would, in some sense, I agree. One thing that can happen though is that I'll explain this in a bit. We often will do a dimension reduction as kind of a first step before we get to this writing down like the APC steps. And so it can happen that I have a problem which is not of this form originally, but then when I do something, for example, maybe there's a one-dimensional sufficient statistic, in that problem. And so then I can convert that problem, which was maybe more complicated than the one that I've described here. I can convert it into this lower dimensional one, and then use the same techniques here to solve that original problem that was more complicated, just using the same tools as here. So I say here, lots of examples can be covered by this, not because they originally are presented in this form, but that they can be converted to this form. So here's just a couple of other illustrations to kind of see how this is going. So I picked two different examples that are not normal or binomial or any of those kind of more familiar types. So one is Cauchy, one is gamma. So here the Cauchy, the parameter is the location, and for the gamma, the parameter is the shape. And so you can see from this, it inherits some of the unique features of that distribution through this formula. So it depends on that CDF. And so then naturally these will be different because those distributions have different CDFs. But like, I mean, the main sort of feature is that, maybe start over here, is that here there's this kind of asymmetry, because like there's the shape parameter of gamma is not like a location that you sort of expect some kind of symmetry to appear. So there's sort of skewness that shows up in this plausibility contour because of the way that theta affects this distribution. But in the Cauchy case, right, it's a location problem. So then like you expect there to be some kind of symmetry, but what's unique about Cauchy is the heavy tails. And so that manifests also in this picture, because obviously the tails are very heavy here. Ranges from like -30 to 30. That's sort of unexpected. Certainly not, it wouldn't look like this if it was a normal distribution, for example. Okay, so then getting to something that's a little bit more complicated. How about if I have IID observations this time? Distribution is normal, mean, both the mean and the variance, mu sigma squared, these are unknown. So I collect them both into this theta vector. So now this is a classical problem, IID observations from a normal distribution. So what would we do? Here I'll give some justification for this in a bit, but what I want to do is I want to start with sufficient statistics. So that's just sample mean, sample variance. So I'll call that mu hat, sigma hat, or sigma squared hat here. Okay, so now this one's two-dimensional, so it's more complicated than what we had just been talking about. So how I can set this up is that I can imagine there's a pair of uniforms, and then I've got these two CDFs, G and phi. Phi is just a standard normal. G is a weird one. So this one is looking at the, you take a chi-square and then you divide by the degrees of freedom. So it doesn't have a nice form, but that distribution is not a problem to calculate. So this G is CDF for that distribution. Phi is the CDF for standard normal. So then I can write that A step, the association, in this way. So there's mu hat is equal to mu. These are very familiar type of expressions here. Where that G comes in is that it's related to the distribution of the sample variance. So that's what's going on is here. And so now, right, we have an association that's in terms of two parameters, basically two data points and two auxiliary variables. So we've matched up the dimension now. But being in two dimensions sort of automatically makes it a little bit more difficult to write down this random set. So what here is the kind of analog of that default one. So it's maybe not clear why I'm taking this to be the, why this is the analog of that default. Let me explain here briefly, is that I'm using this maximum to sort of force these, the focal elements for this random set to be nested. So if you imagine how this random set would look, these are like squares with like a random, so they're squares centered around half, like the 0.5, 0.5 region, and then they're increasing in size. So if I just took sort of independent wouldn't necessarily doing this max operator to force these the focal elements of this random set to be nested. That's important for some of the theory that's later in terms of efficiency and things. So it makes things look complicated here. It's doable, but it's not really nice for writing down these kind of expressions. But the main point I want to make clear is just that I'm choosing this one to force the sets to be nested. It's not necessary for validity, but it's good for efficiency purposes. Okay, so here's a picture. So I just wanted to give you some idea what happens when you do this calculation with that those kind of random squares. So now here I took sample of size 10, and I just set the values here, mu hat and sigma hat, to be 0 and 1. So now what I've drawn here are contour plots of that for that plausibility function. So now it's a function defined on the two-dimensional space. So it's like the function itself is coming out of the plane, and so these sort of nested kind of trapezoid things. These are the contour plots for the plausibility contour function. Okay, and so what you see is that there's 0 and 1, right? So mu and sigma 0, 1, like that's one where like the data is right there. So then this one should be one with high plausibility. And then as you move away from those observed values, plausibility should go down, and this picture describes how they go down. So the red lines here, I wanted to share this with you somehow about sort of the effect of the dimension. So the red lines here are as if I just calculated a 90% confidence interval for mu using like the usual like t-test type of thing. So it's like the mu hat plus or minus something proportional to the those critical values from t distribution. So these red lines represent that. If I were to, so remember how the marginalization goes in this case is that you would look for all of those, in this case, mu values that correspond to a joint plausibility contour that's maybe more than 0.1, right? If I'm using 90% interval, I would look at 0.1 as alpha. So now what that would correspond to in this picture would be to just basically find this corner and this corner and drop it down onto the mu range. Okay, so when I do that, I drop these guys down, right? I see the interval is now quite a bit wider. So it's like something around -1 to 1, a little bit wider than that. Okay. And so what's going on here is that there's a price that I'm paying for having to be valid for every assertion about mu and sigma. Now, when I go and I try to marginalize to this, a very specific question just about mu, I pay some price for that, right? So the price I pay is that I get some wider intervals. I'm less efficient than I would be if I knew from the outset that I didn't care about sigma. Okay, so this is related to this idea about efficiency is related to how we do this marginalization. So if I can't at the outset determine that sigma is not important to me and that I only care about assertions for mu, I have to construct this joint thing. And in order to be valid in order for the joint thing to be valid means I have to sacrifice some efficiency on mu just for assertions specifically about mu. So it is possible to recover this loss of efficiency, but we have to think carefully about the marginalization. This is kind of the trivial marginalization that comes out of the just from this possibility theory, but we have to make some adjustments if we want to recover this loss of efficiency on the mu margin. So that's where we're headed next. How do we kind of force how do we ensure that the results we get are both valid and efficient? Okay, so I mentioned this kind of intuition before, but if I were to just take the random set to be the whole space, so I don't even try to do a good job, then validity is satisfied. So it's not enough just to be valid because this can always be trivially satisfied. How this kind of manifests when you push it all the way through is that you get this kind of vacuous type of belief that assigns plausibility 1 to everything. And so that's not useful. So we want to kind of think more carefully about how do we decide what kind of random set to use so that we're both valid and efficient, that there are some assertions which are assigned relatively small plausibility because we know that they're false. Okay, so then we have to do this kind of balancing act now. So I need, in order to achieve validity, the random set has to be big enough in some sense. But then if I take it too big, it's inefficient. So this comes down to kind of dealing with somehow the size, right? So I want to take this random set to be as small as possible so that validity is still satisfied. So that's roughly what I mean by efficiency here. So this is, we know some things about efficiency and optimality, but this I think is an area that still is I mean, definitely is incomplete. Basically, the only thing I know, and I've already said it, is that I have no reason not to choose random sets that are nested. So what the theory basically says is that if you take a random set that's not nested, there's another one that is nested that's at least as good in this kind of sense. So I'll leave you to look at the specific statement of the result. It's not so important for what I want to say here. So this just means that all I really know is that I should be looking for these nested random sets. But beyond being nested, it's kind of a mystery. So we know some things, but not so much. So this, I think, would be an area where work definitely needs to be, still could be done. What I want to talk about here is more about the dimension. So how I can avoid having to deal with kind of specifying shapes of this random set in the high dimensions is to just figure out ways to reduce the dimension at first. So there's this, maybe you've heard this phrase, a curse of dimensionality. I think everybody says it differently, but I wanted to kind of cover as many situations as I could. So I said roughly what I'm saying here by curse of dimensionality is that everything is more difficult in high dimensions than it is in low dimensions. So if we think about what we might have to do, if we just were sort of naive about how we approach this problem, let's say I have IID samples from some distribution and there's maybe a scalar parameter theta. If I just follow that procedure that we described before, then I probably will have to do something like deal with an n-dimensional auxiliary variable. And that means I need to specify a random set in this n-dimensional space that somehow is good. But because the dimension is high, right, it's possible that I maybe have hundreds of observations, right? So I don't really want to be dealing with this high dimensional auxiliary variable when I only have one dimensional parameter. So there ought to be some kind of way that we can avoid this curse of dimensionality, that we can sort of shuffle this problem around or do some manipulations so that we can actually just focus on a one-dimensional auxiliary variable because the parameter is one-dimensional. So it's basically about trying to match the dimension of u to the dimension of theta. And then once we've matched that dimension, then we're basically in the best situation that we could be. And it's virtually the same as what I was talking here, is that here I started with n samples with a two-dimensional parameter. And I said, well, let's just forget about everything except for sufficient statistics and then do the construction there. So I did that dimension reduction kind of behind the scenes. I didn't tell you what I was doing there, but by doing it this way, I was able to avoid writing down n auxiliary variables. I could just directly jump to writing down two auxiliary variables. And that's better than n because of how I described here curse of dimensionality, that it's harder to deal with n-dimensional thing than it is a two-dimensional thing. All right, so this is the kind of first part of this dimension reduction considerations. So I wanted to, instead of just telling you sort of how it looks in general, try to give you some intuition by looking at a simple example. So here is a case basically like the normal mean type of problem, but it doesn't have to be normal, but anyways. So this is where I have each y is a theta plus a u, and the theta is the same, but I need different u's for each one. So I have n u variables, n y variables, but only one theta. Okay, so one way that I can imagine trying to approach this is we have this system of equations here, y equals theta plus u from I1 to n. So now that's a system of equations. We can do algebra on it. We can manipulate this system however we like, as long as we're following the rules of mathematics. So one way that we can do it is like this, is let's write it as here's the sample mean of y. And if I take the sample mean of y, then theta is the same for every one. So I have equals theta plus, and then sample mean is linear. So this would be the same transformation to the u. So y bar equals theta plus u bar. Right, and if I'm following these algebra rules, I have to make sure that the whole system maintains. All right, so if I can ensure that this system remains valid by writing the rest of the equations this way. So I can essentially do some kind of subtraction. But anyways, this is like on this side I have y minus y bar, and this side I have u minus u bar, and there's n of these equations. So this thing here is equivalent to this system there. Right, so a new system, this system, they're equivalent. The reason why I might consider the second one is that the main thing is that there's no theta in this second line. So what does this mean? It means that there's actually some function of the u's that I observe. Right? Originally, we said this u, I don't observe it, so I would need to have a random set to try to predict or guess that value. But when I do this manipulation, now I see that there is some feature of that u vector that I observe. It's basically these residuals, right? So that this function of the u's is equal to this function of the y's. I observe the y's, so I see this value, which means I know this value of u. Okay, so now when I mean, this has a couple of important consequences. It's that, well, first, in this line, I've now reduced the dimension because this u bar is one-dimensional, theta is one-dimensional. So I've possibly identified a way to reduce the dimension. The second thing is that this information that I have, that this function of u is equal to this function of y, gives me information about the u. And so I could generally use that information to assist in my prediction of this u bar, prediction in the random set sense. Okay, so I've potentially reduced the dimension and added some information that can be used to sharpen the prediction of that lower dimensional thing. Okay, so all we have to do is think about kind of how can you abstract this idea. So that was for a simple kind of location problem. And so this is probably what you would do even if you, weren't really thinking about any of these, cursive dimensionality and all of that. This would be a very natural thing to do. So if you think about how we can abstract this so that it's not just for that location parameter problem. So I'm starting here with this sort of generic assertion or association, y equals function of theta u. Now let's suppose that I can find two pairs of functions. So there's a th pair and a tau eta pair. The t and h apply to y and the tau and u apply to u. So that I can rewrite that sort of baseline association in this form. So it's the function of y is equal to some function of theta and tau u. And that then there's another function of y, which is equal to a function of u. Okay, so this part here on the right-hand side is exactly like what in the previous page, this like residual thing. So this is the function of u that's observed. And then this is the thing that only has theta in it, but some lower dimensional feature of u. Okay, so very often we can arrange these things so that this t and tau have dimension the same as theta. So then I would have effectively reduced the dimension as best I can in the same way that I did here, that there's a one-dimensional theta, and now I have a one-dimensional function of u and a one-dimensional function of y. Okay, so because, like I said in the other example, so there's no theta here, so this gives me information about u that I can use to help with my predictions or guesses of this tau u. Okay, so what that means is that I'm going to do some kind of conditioning. And so it's a little bit messy, this notation, but I hope that at least the idea is clear, is that I've just now forget about the y and the u. I think about just a t is equal to b theta v. V is this new auxiliary variable. And the distribution of v is the derived distribution of tau of u given eta u is equal to the observed value. So I have this is how I'm using that information in what's observed about u to kind of sharpen my inferences or predictions about v. Right? If it was in this previous case and everything was normal, then the u bar is independent of this residual vector u minus u bar. So then this conditioning would have no effect. So in many cases, the conditioning just disappears. But there would be other cases where it stays, and you actually need to do the conditioning if you want to preserve all the information in the original data. Okay. So this is like a first step that one would take before actually introducing the random set, is you first reduce the dimension of the problem so that now I'm dealing with this lower dimensional v, and that simplifies the specification of a sort of quote good random set for this auxiliary variable v. Okay, so if we're obviously now the question is, right, this whole thing hinges on being able to find this th and tau eta. So things that we can do if we have the sort of quote regular problems, you can find the minimal sufficient statistic T, and it has the same dimension as the theta. And because of the basically the definition of sufficiency, you can just ignore the other pieces. And so it just boils down to using a association for the minimal sufficient statistic, which is what I did here. So I said, let's start with this minimal sufficient statistic and just go from there. This is justified because of the theory in this paper and in this chapter 6 from the book. It says if you can reduce down to minimal sufficient statistic that has the same dimension as theta, then that's the best you can do, and you just go from there. So you form your association based on the distribution of that minimal sufficient statistic. There's other cases which I don't want to get into where you have certain kind of symmetry in the problem. So where there's a kind of a group transformation structure. In cases like this, there's ways to do this. And so it's using notions of like equivariance and like maximal invariance of and this has to do with groups of transformations that correspond to the structure in the model. So I don't want to get into that, but this is one other case where there's fairly general theory about how to identify choices of T and H that would solve the problem. So one thing that's kind of unique to it's a thing that I guess could be applied in other contexts, but I think it feels most appropriate in this context is actually working with a strategy that uses partial differential equations. So I'll preface this by saying I know essentially nothing about PDEs, but I think there's some nice intuition, and often you can, if necessary, you can just sort of solve these problems without having any real special knowledge of this. So I'll say a few things about this, but try not to get too messy. So remember, there was this, I defined this earlier, this u of y theta. That's like, that's like the unobserved value of that, of the auxiliary variable. So let's just think of this as an equation. I set y equals to a theta u, and then I solve it for u. So then this is the solution to that equation. So what I want is for this a to u to be a function that I observe. So it's like that. Right, so I want to find an h such that eta of u is equal to some function of y. So I can observe that value. So what would make it observable is that it doesn't depend on theta, right? That if I imagine plugging in this u y theta into this eta function, that it would be constant in theta. It's not sensitive to changes in the theta for fixed y. Okay? So then what this eta is actually corresponds to is one that is a function that would satisfy this differential equation, that if I differentiate this function with respect to theta, so this is like I put the u y theta inside and then eta on the outside, differentiate with respect to theta, this would be equal to 0. So there's no sensitivity to the to changes in the parameter. Okay, so I don't know how to say whether this exists in general or not. I generally don't even know how to solve it. There are some ways that you can solve it, like formal ways. There's this thing called method of characteristics. I don't really know anything about that, and that's not really my domain. But there are cases where you can solve it, and so it's at least it's a useful technique, and how useful it is, I don't really know, but this does provide some kind of way of identifying this eta function. And maybe I have it somewhere, but all of these functions, th, tau, eta, they're all kind of connected. So if you know one of them, you can usually figure out what the other ones are. Definitely if you know both eta, tau and eta, you can figure out t and h. But I think it's actually just one of them defines all of the others. But anyways, so if you can find this eta, you can usually solve that problem of identifying th and tau eta. So this has been particularly useful in cases where you're actually not able to use sufficiency to reduce the dimension down to exactly the dimension of theta. So yeah, I have an example of these things. I don't know if this is how familiar this is, but so there are cases, I guess classical example of this is like if you have a uniform model and the parameter of the uniform, so the support of the uniform is like theta to theta plus 1. So it's like, you know how long the interval is, but you don't know where it's located. So in this case, the sufficient statistic is 2-dimensional, but the parameter is only 1-dimensional because it's like theta to theta plus 1. And so this is kind of a classical problem of one where sufficiency sort of fails because you can't reduce down to something exactly the dimension of the parameter. So it's these kind of problems where I've found this PDE approach to be useful. So this is going back to that original that example we had looked at before. This is just where y is equal to constant theta plus a vector of u's. And you can solve this equation for u is no problem. And then you just want to do, set up that kind of PDE. So you can do this chain rule type of a calculation. So what I want is a 0 over here. This is a vector of zeros. And then I have this 2 derivatives that are kind of multiplied. So this will be a matrix, this will be a vector. This du d theta is easy to get because it's just here. Now then what we want to see is that this thing is going to be a constant vector, and this is a matrix. And so I just want to make it so that this matrix takes constant vectors to 0. So then that sort of makes us think about like orthogonal projections and stuff like that. And so it's relatively easy to figure out that the eta needs to be of this kind of form, where this M is like a projection onto the space orthogonal to the space, projects onto the space orthogonal to constant vectors. And that's what this does. So that means that all we've done here is then if we sort of plug all this stuff in, then it's like that u minus u bar is equal to y minus y bar. That's what we derived before. So this is one kind of simple case where you obviously wouldn't employ this kind of heavy machinery to do it, but that it can be done and that you can actually figure these things out. So the main reason why I wanted to mention this is that this is useful in these non-regular problems. And what often happens in these non-regular problems is that you can't really solve that PDE exactly how I said it, how I formulated it. It's that you often need to bend the rules a little bit and look for what I'm going to say here is sort of local solutions to the differential equation. So this localization is important, not necessarily for what I want to say now, but what I want to say a bit later. So let me just describe this here, and it actually has nothing to do with the PDEs, but often this is how I was approaching this problem was with the PDEs. Okay, so here's the kind of a generalization of that approach that we just described about kind of to reduce the dimension down by conditioning on some observed feature of the u variable. Okay, so let's suppose I can do this, and so I fix this point t, so t is some value in the parameter space. And let's suppose I'm going to rewrite that original kind of baseline association in terms of it looks very much like what I've written before. The only difference is that there's t here. So I'm allowing this part to depend on that specified localization point. And so what I want to do is I'm going to do all of the same stuff, but now t is kind of like a parameter in this. So it's like the whole construction will be t dependent. So I ultimately will get some kind of random sets and some kind of upper and lower probabilities, but these depend on t. Okay. So I've sort of highlighted that t dependence here. So it's just that plausibility contour function, for example, now depends on t. So what I'm going to do is I'm going to do what I'm calling here fusing them. So I'm going to fuse them together by whenever I want to use whenever I want to evaluate this function at a particular theta, I use the same theta as the localization point. So I'm sort of cheating here. I'm taking these this kind of class of t-dependent inferential models, and I'm fusing them together so that in this particular way, so that if there's theta here, then there's theta here. Okay, and so if I do it this way, right? So I didn't explain this completely. So what I'm doing here is I'm going to arrange so that these are valid at the particular t. So it's t dependent, and the construction guarantees that they're valid. And then I want to take I want to fuse them together by setting t equals theta when I'm evaluating the thing at theta. So maybe the easiest way to look at this is that I can calculate what is basically a possibility measure. And I'm doing that by putting this theta parameter here on both sides of the vertical bar. So this is the fusion part, is that I have, this is dependent on some localization point. And I'm choosing that localization point to be the same thing as the argument that I want to evaluate it at. And so as long as I can do this, the max of this function is equal to 1 for every y, that does define a possibility measure. So I'm defining this thing a fused plausibility function, which is of this form, just doing this optimization. So I wanted to show one kind of quick example of this. I'm not really showing any details here because I don't even remember how I solved this. So the problem is one like this, and I learned about this, actually Teddy Seidenfeld told me about this problem a while back. It's kind of it's a weird problem, but one where there's some challenges in trying to do the dimension reduction. So it looks kind of like that location parameter problem. The difference is that this one is theta and this one is, cube root of theta. So that, because there's this kind of nonlinearity, you can't actually reduce the dimension at all. So sufficiency only says keep y1 and y2. You can't do anything. But I was able to work out this kind of PDE trick and do this kind of localization. So this makes this messy formula, like who cares what that function looks like, but we can draw some plots and we can kind of see what's happening. So what's going on here is there's basically two observations. There's a y1 and a y2, right, that comes from this kind of structure. And so if I just used y1 and built a plausibility contour, or if I just used y2 and I built a plausibility contour, ignoring the other one. So that would correspond to, the first one kind of is, so y1 has no cube root transformation. So if I use this value of y1, I can construct my plausibility contour for theta, and it's pretty tight because there's actually a good amount of information about theta in this y1 observation. If I go to y2, there's like much less information in y2 about theta because of this weird nonlinear transformation. So having not very much information manifests as having a wide plausibility contour. So this other dotted line is the plausibility contour based on the y2. So there's not really, these two things, neither one of them is really great because they're ignoring the other part. So this fusion, what this does is effectively kind of combines those two separate plausibility contours into one. And the solid line here is the one. It's just a plot of this ugly looking thing here. And you see kind of what's happening is that it's kind of a compromise between the tight plausibility contour coming just from y1 and the really wide plausibility contour coming from y2. So through this kind of fusion and combination type of step, these things are now put together, and this would give you a valid inferential model that combines the y1 and y2 in this way. And so it's based on, you essentially can work down to a one-dimensional type of auxiliary variable, but you have to do the localization trick. I won't really say anything about this, but there's one example that's kind of a classical one in statistics about trying to do a good job of marginalization. Or, well, it's a non-regular problem where the sufficient statistic is two-dimensional, but the parameter is one-dimensional. So it's a bivariate normal. The means are 0, the variances are 1, but the correlation is unknown. So it's surprising that this is kind of a complicated problem. But there are a number of sort of proposed solutions to this. And all I wanted to say here is that, so there's a Bayes solution. There's this one called R star, which is actually from one of the methods that Don Fraser was strong supporter of, was basically higher order type of approximations of likelihood ratio statistics. So this is a very good solution. So both the R star and the Bayes solutions are actually quite good in this case. But this is just one situation where we can see that if I'm doing that kind of fused inferential model strategy, can actually do better than many of these very good methods with a higher order type of asymptotic approximation. So there's just some numbers there. You can, it's probably better to look at the paper for some context about this, but anyways. Okay, so I think this is my kind of end of the part about the conditioning step. So I just was going to mention a couple of references here. So this dimension reduction is important because we're trying to achieve efficiency. So we don't need to do dimension reduction for validity. The dimension reduction is for efficiency purposes. So what I described here, basically, if you can use the things with sufficient statistics, all the standard examples have the nice reduction through sufficiency. So what I proposed here can handle all of those problems. If we're dealing with the non-standard examples where sufficiency isn't good enough, you can do better kind of using this localization strategy, often coupled with the differential equation approach. So if you were interested in some of these, there's a couple of papers here you can look at where using those techniques like localization plus the differential equations to get solutions to some non-regular type of problems. So valid and efficient solutions. Okay, so I want to turn to a second type of dimension reduction strategy next. So I guess maybe I can pause for a second if there was any questions about the dimension reduction via conditioning before I move on to there. Gives me a chance to take a drink anyways. So, okay, so let's we can jump ahead to the second type of dimension reduction strategies for this marginalization. So the situation like this is a special one. It's not every problem would be able to be attacked in this way. So what's special about it is that there's kind of a decomposition of the parameter into something we care about and something that we don't care about. So I talked a bit about this in the part one yesterday, is that there may be cases where I don't really care about the full parameter. I'm interested in some feature of that. So we looked at, like, the one example was like the Feller-Creasy problem. So we had a two-dimensional theta, but the thing I really cared about was the ratio of the two. So that was like where there was an interest parameter of phi, that was the ratio. And then there's the other thing that I don't care about, which, I mean, you could think of this if you tried to write the Feller-Creasy problem in this way, you could take phi to be the ratio theta 1, theta 2, and then you could take lambda to be theta 2. So then I don't really care what theta 2 is. I don't even care what theta 1 is. I care about the ratio, but all I need to do is to be able to write kind of an equivalent representation of theta in terms of thing I care about and thing I don't care about. So one example that we've, I think, mentioned already is that I might have a parameter that's like a mean and a variance pair, and I might care about the mean more so than I do the variance. So then I would want to be able to marginalize out the variance to get to the mean. Okay, so what happens now is that, I mean, just like before, there was like a one-dimensional parameter or some low-dimensional parameter and maybe a high-dimensional auxiliary variable, and I wanted to figure out ways to sort of reduce that dimension down to simplify the random set specification and also to gain efficiency. So here the situation is the same, but it's not in terms of the, I mean, it's that we may have already reduced the dimension of auxiliary variable to the dimension of theta, but I can actually go further because I don't care about all of theta, I only care about phi. So maybe there's an opportunity to push the dimension down even more to increase the efficiency. So that's this marginalization strategy, is to try to reduce the dimension further so that we can be even more efficient about the parameter of interest. Okay, so here's how this one goes. I think this is actually simpler than the conditioning that we described before. If we start with this kind of baseline association, the relationship between y, theta, and unobservable auxiliary variable. But let's suppose that we've done, this is now post-conditioning, so that the theta and the u are of the same dimension, so that we've already done all the things that I described before. So now the question is that, okay, the theta is not fully of interest to me. I only care about the phi component. And so I want to reduce the dimension more. Okay, and so here's how I want to write this, is that I want to be able to convert that y equals a theta u into an expression, a pair of expressions like this. Left side is a function of y and phi. Right side is function of phi and a variable v1. Then the equation is one that's a function of y, v2, phi, and lambda. then this is equal to 0. So the way to write it is just that this thing is equal to 0. So that it doesn't matter which side things are on, basically, that if you have a y over on the left and some other things on the right, you can move everything to the left and then have it be equal to 0. So this is different from before. It was actually critical that in the conditioning case that that second equation was like a function of y on one side and a function of u on the other side. Here, which side it's on doesn't actually matter. So it's a little bit more flexibility here. So the critical point is that this function d on the right needs to satisfy a certain kind of property. And the property says that for this triplet, y, v2, phi, I can always find a lambda that makes this equal to 0. So it's this is actually fairly mild, but it wouldn't hold in every case. So it's essentially is that when you fix those other two parameters, you can find this root as a function of lambda. So if this d function satisfies that one, then what I can do is I can just I just ignore this part. So the theory says that you actually don't need to worry about this anymore because it doesn't actually tell you anything about the phi. So there's no information about phi in this expression if this condition holds. So then just throw it out. So if I throw it out, what's happened? So by throwing it out means that I'm only focused on this component here. And now there's this v1 variable, and that v1 variable is usually some low dimensional function of u. So I've effectively reduced the dimension that I'm concerned with because I was able to throw this this other equation away. Right, so here's back to that normal distribution problem that we talked about. So I have IID sample y1, yn, and mu and sigma both are unknown, but I care about the mean. So from the conditioning argument, I can reduce to sufficient statistics. So that's the mu hat, sigma hat, like before. And so what I can do here is I can remember, this is what I had written previously. I guess I've redefined these. No, that's fine. So I'm going to write it this way. So this is mu hat equals mu, and then this is that sigma root n, and the standard normal is there. And then here, I guess I have done a little bit of modification. So I did the square root here. So this is a sigma hat, sigma, and u2. And u2 has distribution of the square root of chi-squared divided by its degrees of freedom. So now I have these two equations, and I only care about mu. So this is how I have some opportunity to reduce dimension. So let's rewrite this thing. And all I'm doing to rewrite it is just, this one has a sigma. I just solve this one for sigma and I plug it in there. So if I do that and then I shuffle some stuff around, so then I have the root n is over here, mu hat and mu, and the sigma hat. So this is a function of the data and the mu. Over here is a function of just auxiliary variable. And this one is a function of the same thing. So sigma hat, sigma u. So I can always, if you give me a sigma hat and a u2, I can solve this for sigma. I just just divide it. So there's no problem here to say that this second thing can be ignored. And so when I ignore the second thing and we look at just the first thing, I can now unwrap this and we see something very familiar. It's that now the mu hat is there, mu plus sigma hat, root n, and v. And this v has a distribution of u1 over u2. And u1 over u2 is exactly a t distribution. So this is the way that we can actually strategically do that marginalization so that we can eliminate the sigma part, but without losing efficiency about the mu. So that's the main idea here. So remember, if we, sorry, it's a bit far to go back, but in this case, we had a joint kind of inferential model for mu and sigma. And if I do naive marginalization, it's not efficient because the red lines are much narrower. That creates a much narrower interval than if I just project these corners down to the mu space. So by applying this strategy here, I can do that marginalization in a strategic way. And now I've lost no efficiency. So when I do this, when I find this kind of a plausibility intervals for mu based on this formula, it'll be exactly those ones from that we know are sort of the best coming from the t distribution. Okay, so I have a question here from Dominic. right. So this U2 can never be zero. It's coming from this kind of distribution. So the U2 can never be zero. So that's one case where I mean, obviously if it were equal to U2, then, right. Okay. Yeah. Yeah, right. Okay. So yeah, there's no issue. I mean, if there may be some, I guess, probability zero events that where there's no solution, but that's of no consequence. Yeah. Yeah. Good point. All right. So this marginalization strategy tells us how to eliminate the sigma and not lose any efficiency in terms of the mu. There was that Feller-Creasy problem we talked previously. So that's where the interest is in this ratio of theta1 to theta2. So there's a section in book and also in one of the papers about this. So how we can do this is as follows: is that so remember theta2 is lambda and theta1 over theta2 is phi. So a way that we can rewrite this one is that to think of the theta1 as the product phi times lambda, and then the theta2 is lambda. So this is a convenient way to write this. So now we can start shuffling some things around. And so in particular, if I do like a subtraction of the two equations and then kind of a standardization of that. So that I do the same kind of subtraction and standardization on this side. So now this thing is just a function of the y's and the phi. And over here, there's a function of some, y lambda u equal to 0. So again, I can always find a lambda to solve this equation, regardless of what y1, y2, and u2 are. So that one can be ignored. You have to think a little bit about this. It's maybe not immediate, but that this thing in blue, I actually know what its distribution is. It doesn't depend on the phi. So this turns out that this is actually a standard normal. This thing has a standard normal distribution. So I can just forget about that expression, just call it a v, and use the standard normal v as its standard normal as a distribution of v. That is its distribution. So then I can rewrite this whole thing in a very simple way. There's this kind of complicated function of data and phi over here, but on the right-hand side is a very simple random variable, just a normal. So I can use really any of those kind of standard type of random sets for predicting this unobserved value of v, and that will lead to a nice and efficient kind of inferential model for the phi. So here's kind of what some of those, what some of that output looks like. So here's just a couple of cases, different data sets, so you can kind of see different things going on. But like in this particular case, this is sort of quote nice data, and so then we're interested in the ratio, so you can kind of see that if you look at the ratio of this, it's maybe around 2, and so then we would expect this guy to be kind of spiked around 2 and then decay on both sides. So the fact that these guys are both kind of away from 0 makes it sort of nice. If over here the data is not so nice, it's that you have one thing is kind of away from 0, but then this one is kind of close to 0, closer than this one at least. And so having this other observation kind of close to 0 throws things off. And so you end up getting a very oddly shaped kind of plausibility contour here. It's not a problem with the solution. It has to do with sort of the difficulty of this problem, is that it's actually not possible to always have bounded plausibility intervals that satisfy the kind of desired coverage probabilities. So you need to have some kind of weird shape like this if it's going to be valid. So this is something that actually has to happen if validity is to be achieved. And so it's nice to see, actually, even though it's weird, it's nice to see that it happens because it's necessary to happen in order to have the validity property. Okay. So question, does the right side reach 1? So if you were to extend this thing over to the right, it stays bounded. So it doesn't get much higher than what it is now. So it'll eventually just kind of, yeah, sorry. So the scale here is not right. So yes, this does hit 1, yeah. Yep, yeah. Okay, I don't have, okay. Actually, so I think now maybe is a good spot to stop for this first session. So then we'll come back, I guess, to Mark would probably say something about it. So there's take some break and then come back. I have a few more things to say about marginalization and then on to part 3. Yeah, thanks for coming back. So a little bit, I think was a little bit heavy. I apologize for that. I think we'll have a little bit more heavy and then we'll be more high level again. So I wanted to do one more example. So that we were talking about this kind of marginalization strategy just before. So where we can do a rewriting of the kind of the baseline association, which has potentially high dimensional auxiliary variable. We get this down to something to eliminate some nuisance parameter and also to reduce the dimension of the auxiliary variable we need here. So we did a couple of examples already. The one I wanted to do next was related to this. It's actually related to that satellite collision problem I talked in the last in part 1 yesterday. So often goes by a name like a many normal means. So it's in this case maybe we have an n-dimensional case where a little bit mistake there. So it should be y equals theta plus u, and this just means that there's a vector y, vector theta, vector u. The u is a normal, let's say variance is known and they're independent. So the quantity of interest here is actually the length of the theta vector. So how does this relate to that like satellite problem? So what we were looking at there was basically the theta was the difference between the centers of the two objects, like satellite and another satellite, or satellite and some whatever space garbage. And so then there would be a collision if the distance between these two things was sufficiently small, right? So like each one has some radius, and so there's like some distance that if they're within this kind of proximity, then they're going to be a collision. If they're not, then there won't. And so that's this kind of context for the satellite problem. But this turns out to be actually a challenging problem, anyways. So what's going on here is that we can write the theta basically as a product, and phi is the length, and then lambda is like the direction. So then this thing lambda is just some vector on the unit n sphere. So we were talking before, this n equals 2 case is the satellite collision problem, but you can talk more generally about any kind of n, finite value of n. So actually it's a little bit complicated here, but it's possible actually to reduce this down to a very simple kind of a reduced association that's directly in terms of the interest parameter, the phi. So it looks just like this. There's this non-central chi-square distribution that's showing up. So you can get this down to a one-dimensional problem. There are some things that you need to be careful with, and I won't go into that here. There are just some kind of minor details, but that it does make some difference. So I'll skip that, and I'll just show you some kind of results from this. So you might remember back in the part 1, I showed you some plots kind of like this, and actually the only difference here, the black lines on these plots are the same as the ones I showed you yesterday. So those are the collision probabilities or non-collision probabilities as a function of the error, the sigma. And what we said last time was the sort of the problem, or where this kind of false confidence phenomenon was sort of manifesting there, was that it didn't matter what the data says. If there's enough noise, then you eventually think the satellite is safe. And so that's kind of seen here by the black line kind of approaching 1, really no matter what the data says, if the sigma is sufficiently large. So here, what I'm doing is now there's some red lines drawn on there, and the red lines are based on the marginalization after, so using this kind of IM construction to get a marginal association, introducing random set and getting the corresponding lower and upper probabilities. So these red lines correspond to the, so if pi of y with no bar, that's like the black line. And then there's this lower bar, upper bar. Those are the corresponding red lines. So lower bar is solid red, upper bar is the dotted red. And here you see, actually, there's a much more natural kind of interpretation of what's going on here, is that as the data gets more noisy, it's not as if somehow there's more support for non-collision. What's happening is that you just don't know, right? There's more and more you don't know. You have sort of more uncertainty about what's going on, and that's clear from how the two lines separate. right? So you see that this like lower and upper probabilities are pretty much the same when the sigma is relatively small. So it's like, that's actually a pretty informative situation. But then there's a certain point at which now you basically lost information to be able to make any sort of precise inferences. And so then this the two curves split. And so now you see that this lower probability, of course, is going down because you have there's no support for non-collision in the data, but you also can't rule it out. So it's sort of, it's neither believable, it's not believable, but it's definitely plausible that there would be that there'd be non-collision. So this to me is actually a much more informative kind of picture. As you see, what should be happening is when the noise increases, you just don't know. And so that's actually represented here, I think, pretty clearly by the separation of these two curves. Whereas the Bayesian solution just says, well, if it's noisy, then they must not be colliding. And that's not a reasonable conclusion. And then so here I also had shown you some kind of this was more specific to that false confidence type of phenomenon, was we can look at actually the distribution of those, the belief assignments. So we can talk about the belief assignment by the probability measure and also by this lower probability measure. And what we should see is like, so validity requires that if we're looking at a false assertion, then that probability or lower probability should be not too small, or sorry, not too large. And so this was the same picture I showed you before, just with the probability of non-collision. And what happens is that if the noise is sufficiently large, then you just always say that the non-collision probability is high. Whereas what's going on here, sorry, the axes aren't the same, but what I'm showing here is the CDF for this random variable, lower probability of y, and that lower probability is based on the construction here. And what you see is that when there's small noise, right, this belief to non-collision actually is relatively small, right? So here this situation is that the data are generated as if there's going to be a collision. So I should, if they're actually on a collision course and if the data is informative, like if sigma is small, then I should be seeing these lower probabilities should actually be relatively small, right? And so this being kind of above this uniform like this is an indication that it is relatively small. But as you get more and more extreme, like more and more noise, what happens is that sort of the worst that you could ever have is just on uniform. So this uniform is kind of becomes like a bound. So you can never go past it and be invalid. But if you happen to have informative data, you could be a bit more efficient in the sense that you're able to detect that this is actually a collision event. And so the beliefs assigned to non-collision should be relatively small. Whereas the Bayesian solution can't do that. It just always just assigns large values and is not informative. Okay, so I guess to recap about the marginalization. So the strategy here was like, if I recognize that there's a particular quantity of interest and I'm willing to commit to not caring about the other thing, then this gives me a way to reduce the dimension down even further and to improve efficiency. So there are cases where that there was the one condition that I mentioned about how if this could, if it was related to that D function. And so if that D function satisfied something, then you could just ignore it. There are cases where this isn't possible. And so one classical example of this is it's called the Behrens-Fisher problem. That's one where you have two samples, like two normal samples. There's like an X sample and a Y sample. They have different means and different variances, and you want to test if the means are the same. So that's the Behrens-Fisher problem, is this inference on the difference of the means. So that particular problem, there's no way to solve it using the theory that I just described. But there's a generalization that we introduced in paper that gives a way to deal with this. It's a little bit more complicated. We actually, I think, except for the couple examples that we did in this in the paper, probably hasn't been investigated at all. It's one of those things it's interesting, but I never really found time. So I think that would be interesting to look at if there's better ways to do that, more efficient ways to do that, easier ways to do that. I just don't know. So I mentioned at the beginning the outline. So I've finished now this discussion about the dimension reduction things. So there's one kind of technique that I was able to come up with that seems fairly simple, And it actually leads to, I mean, pretty easily to things that are these valid inferential models. It's unclear to me whether we're actually losing something in this formulation compared to what I just described. Again, I think that would be of some interest to investigate. But how this one goes is says, well, that those dimension reduction steps are maybe not so easy, right? You can maybe anticipate that because the one explanation I gave was using some partial differential equation, right? That's probably not such an easy thing to formulate. So if there was some way to do these kind of, reduce this dimension to make things more manageable, if this could be done in an easier way, obviously that would be attractive. So what I thought here is that you could just forget about, as the starting point, actually trying to describe the distribution of y in terms of theta and u. So that original setup was thinking like, let's describe how the data are generated and then from there work towards some kind of valid inferential model. What you could do is say, well, I forget about this exactly describing the sampling distribution of the y. Why don't we first reduce the dimension by just considering some real valued function of the y and theta? So a reasonable thing, and this is what I've used in some of the papers, is to define this function of the y theta as like a likelihood ratio. So this is basically the likelihood at a particular theta value and the likelihood at the maximum, at the maximizer. So this would be a ratio that's less than or equal to 1. And so then take that thing as kind of like your starting point, and then, then you can construct a kind of a plausibility measure, which is essentially a p-value based on a likelihood ratio test type of idea. And then this one would have some kind of consonance property, and you construct the possibility measure in this way, doing optimization. So at the time when I was working this, I didn't even know about possibility measures. So maybe this is a fairly straightforward thing, but actually we're able to do, I think, a number of nice examples with this. So I won't talk about any of those details, but so things about, I think forget which one of these. So something about meta-analysis, doing some kind of like combining the data coming from different studies. We're able to do something using this kind of framework. Interested in some kind of more general type of thing where there's not using a model. So like an example is like if you wanted to do something like, if the quantity you were interested in maybe is like a quantile. So maybe I would like to learn something about the, maybe the 90th percentile of some distribution. So the 90th percentile has actually nothing to do with a model. So you couldn't really think of like the 90th percentile as like the parameter of some model. It would be more natural to think of this kind of in a model-free type of framework. And so it's easy, of course, to estimate quantiles. You can just use the sample quantiles to estimate them. But how do you quantify uncertainty about those things? You shouldn't have to introduce a model first and then do all this marginalization thing to get down to this particular quantile. It'd be best if you could formulate the thing directly in terms of the quantile. So my student, Leo, he might be here now. So this one thing that he and I are working on now is kind of directly get into these like a valid inferential model about a feature of the full parameter, for example, like a quantile of the CDF. So there's a sort of all along when I was thinking about these things, it felt as if it's almost like cheating, that you can basically avoid some of these like dimension reduction steps. And that somehow to get to this extreme kind of dimension reduction, you must be losing something somewhere. So I'm not entirely sure about that. That's just my kind of gut feeling. They're still effective. So it's actually a nice, pretty simple type of strategies, except for some computational issues. Actually fairly straightforward to get these solutions, and they seem to work well. So I'm not really sure. Maybe my gut feeling is wrong, but that's, I think, would be an interesting question to look at. And so then one other problem I wanted to mention is in prediction. So prediction is one where you care maybe about like the next observation. You don't care about model parameters. So you could think of this as kind of an extreme marginalization problem where, in fact, the entire parameter is nuisance, and you want to you're interested in the next realization from the data generating process. So you can do these things in the formulation I described earlier. You just basically apply the marginalization and then you eliminate the whole thing involving theta. That is possible, and so this 2016 reference describes how that can be done. I think more interesting, I think recently, again, my student Leo, we were working on something related to Schaefer and Boff's conformal prediction. So that's actually a very powerful strategy for prediction. And we realized that actually there's a way to represent the conformal prediction in terms of these inferential models, and that you can sort of treat so the conformal prediction is focused on returning prediction intervals. So there's a way that you can kind of convert the conformal prediction output into a what is effectively a possibility measure, and then it becomes an inferential model that has these kind of validity properties. And so that was kind of interesting. So this was quite recent, actually. So I guess technically 2021, but we probably first version was 2020. So that's, I won't say anything about the details, but that's actually some recent work that I'm pretty excited about. So last thing I wanted to do for this part 2 was go back to that characterization theorem that I mentioned at the end of part 1. So what that one, more or less what that said is that if you start with some kind of a frequentist procedure, then you can find some kind of a valid IM, which had something to do with these possibility measures, and that it would result in procedures which were no worse and could, in general, were more efficient than the one that you started with. So there's actually more that can be said, and it has to do with the structure of that, the valid inferential model that's constructed in the proof. So what I said before was just that there's some kind of a possibility measure, or consonant plausibility function that was then there, and you could derive the procedures based on that possibility measure. So it turns out there's actually more going on, and it's that there is a random set on the U space that corresponds to this plausibility function, possibility measure. So it has to, there's some connections to those random sets on the U space, and some this kind of fusion step that I mentioned earlier about. I did the fusion thing kind of in the context of that PDE, but that's not really why I wanted to do it. It's because it shows up here in this characterization theorem. So what we can do is we can imagine kind of a generalization of what I said before about this fusion, is that imagine you have actually a family of random sets. And so this means it's just indexed by some t. T is some value of the parameter, say. So what I have going on here is that it's the same random set, but now its distribution depends on this t parameter. Okay, and if I go through all of those kind of constructions, same as before, I can end up with let's say here is like my plausibility contour, and this depends on t, and it's just the same deal. To find the distribution of that random set here, check whether it contains this generic value of the parameter, but this probability is evaluated with respect to this t-dependent random set. So now what I want to do is I want to fuse them together, or fuse this kind of family of inferential models together, and doing it in this kind of way. So it's basically, like I mentioned, is that you have a particular argument that you'd like to plug into here, and you just force that parameter to be equal to that argument you want to plug in. So in order for this all to work, you have to satisfy some condition here about that. If you put those two guys together, same value, that you can find such a theta that will make this equal to 1 for each y. So it doesn't have to be the same theta for each y, but that every y you can find such a thing. And then you just define this thing using the consonance property. So just you compute plausibilities by maximizing this plausibility contour over the assertion. So again, because of the supremum operation here, you can easily check that this fused thing would satisfy validity if each of the individual ones do. So that's another kind of interesting result related to this supremum operation. So I'm going to just think of this as kind of a family of random sets and a corresponding family of valid inferential models. So then this is the sort of restatement of that theorem I mentioned last time. So it looks like this. So we start with some kind of family of confidence regions for this interest parameter. So not about the full parameter, about the interest parameter. And it satisfies this kind of coverage property and the nested property. So we talked about that one last time. There was a compatibility condition, which I left off. Again, I'm sort of leaving it off, but I coded it here in blue because it's related to this. So this condition here is something we have to actually verify. And so then there's something about the relationship between the association that I'm going to use, that like y equals a theta u, and this form of the confidence region. So this is what I'm calling compatibility. It's compatibility between the association and the confidence region. Basically means that there exists an association that's compatible with the confidence region in a particular sense. So it's not interesting, so I just didn't show it. It's actually easy to check. So there's a number of, in the paper I say a lot about the compatibility condition. So it's not a particularly strong requirement. So what the result says is, so this is what I said before, there's a valid IM for theta. So again, you get to the full parameter, not just to the interest parameter, but that this particular valid IM is derived from one of those valid random sets on the U space, or perhaps a family thereof, and using the construction that I described above, like in part 2, that gives you this kind of new kind of confidence region that's based on thresholding the plausibility function, and that this thing will be more efficient or no less efficient than the confidence region you started with. Okay, so there's more structure here than in the first version that I gave you. The more structure is that it actually comes from random sets on an auxiliary variable space, and that and through the sort of propagation of that random set on the U space through the model to a random set on parameter space, and that it determines one of these kind of fused plausibilities, and we can construct this confidence region here that will be no less efficient than the one we started with. Okay, so again, there's a version of this also for hypothesis tests. It's not specific to this, to confidence regions. So this again kind of shows it's not just like frequentist and these possibility measures. It's somehow it also has to do with these random sets sitting there on this separate U space. And they're allowed to have this kind of, there could be a family of them that they get fused in this particular way. So I don't know if I fully understand that, but it does seem like there's something important, because that's, I mean, it's in this characterization theorem. So I mentioned this at the end last time, but didn't tell you why this matters. So that the proof of this is actually constructive. So that means that to prove it, I actually go through and say, fine, I construct this random set such that those things are satisfied. So it's interesting, because then what you can do here is you can actually treat that proof as like an algorithm. And the algorithm can then be used to say, okay, I'm going to take as an input some kind of a reasonable frequentist procedure. So any kind of confidence region you can think of that satisfies the conditions of the theorem. Doesn't have to be a great one, but at least it satisfies the conditions of the theorem. Then you can crank it through this algorithm, and the result will be a valid inferential model on the full parameter space, who gives answers about that interest parameter that are no less efficient. So I'm not sure if this might be something that's not so familiar, but if, as an analogy, if you know about this Rao-Blackwell theorem, which is usually presented in the context of like in a stat theory course, of first stat theory course, is a way of taking an unbiased estimator and constructing another unbiased estimator has smaller variance. So this is kind of the, I think, an analogy. That's an analogy to this, or they're analogous, let's say. And so here what we're doing is we're taking some procedure which may not be a great procedure, but at least it's controls the frequentist error rates. And then you can crank it through and you can produce a new procedure that's at least as good. So I wanted to show you just a couple of pictures to illustrate this. The details are a bit too much to show, I think, here. But on the left is a binomial case. And so what I'm starting with is the Klopper-Pearson confidence interval for theta. So Dominic was asking earlier about the Klopper-Pearson. So this is where it was coming up. So what's happening here, there's, maybe it's hard to see, but there's a gray line sort of on the outside. So this corresponds to the plausibility contour for the Klopper-Pearson interval. So you kind of can create a p-value out of the interval and then plot that p-value, and that's what this is. Then there's the black line, which is the one that says, take the Klopper-Pearson interval as the input, crank it through this proof, and then show me what's the corresponding plausibility contour on the outside, or like as the output. Then the black line is that output. And you see that it's inside of that Klopper-Pearson plausibility contour. So if you were to do a thresholding, like to say which thetas are bigger than alpha, then the black line would give you narrower intervals than the gray line. And so that's that's this part about the intervals are inside of the other one. So you gain some efficiency by cranking through this kind of inferential model algorithm. And then the right side, I'm not really showing you anything about how the procedure goes, but there's a difficult problem in statistics, which is about in mixture models. So I might be considering, like, for example, I might have, maybe I'm interested in a model that's like a mixture of several different normal distributions. So this is often done to try to capture some kind of a heterogeneity in the population. So you might want to say, okay, is there really a mixture model there, or is it just one distribution? So you might want to test like one normal against a mixture of normals. So there's lots of tests for this, but no tests, at least until recently, that were sort of provably could control the type 1 error. So the paper that presented this was actually a very nice paper with some general things, not specific to that mixture model problem. Larry Wasserman and a few of his colleagues at Carnegie Mellon. So they developed some kind of procedure, they call it like a split likelihood ratio test, and where this sort of provides some guarantees in terms of the type 1 error, but because it's very general, it's not super efficient. So you can kind of see that here is what's drawn as the power function in gray of their split likelihood ratio test. So it's at 0 is where there's sort of the null is true. So this is where you would expect it to be equal to like the significance level, the type 1 error level. So it's too small. So that's how you can kind of see the inefficiency. So what I did was I took their split likelihood ratio test, I cranked it through the inferential model algorithm and get a new test from that. And then I check what's the power of that test. And then the black line here is a plot of the power function for the inferential model test. And so its higher power is better, but still is controlling the type 1 error here at 0. So it seems like this is actually a considerably better procedure after you crank it through the inferential model algorithm. All right, so then this is I guess, to the end of my part 2. Spilled over a bit into the third session, but that was what I expected. So what I talked about here was this kind of 3-step construction. So you start with an association that involves some auxiliary variables that you can't observe. Then you predict that the unobserved value, or guess that unobserved value of that U variable using some random set. And we have to be careful about how to choose that random set in order to achieve efficiency. But then once we have that, we just push this random set on U space through the model into a random set on the theta space. And then now this gives me some kind of a random set that I can summarize using, say, lower and upper probabilities, so forth. And then this is provably valid, assuming I constructed that random set on the U space properly. And so I talked maybe too much about this dimension reduction, but this is important as kind of a, it's like before we actually do the A step, is that we try to reduce the dimension to simplify the problem of reducing the dimension down, gets rid of cursive dimensionality, makes choice of reasonable random sets much easier. We can do this in a lot of problems, but it's not so straightforward. So, I mean, there is some complication here, both conceptual, at least in terms of a statistics audience, lose them right away when you start to get into the imprecise probabilities and random sets and stuff like that. But on a more practical side, I guess computation can be an issue. And so I guess one thing I'm hoping is that maybe folks here know something about how to do these computations in some kind of general way. But we can talk some more about that. So a couple things I postponed till the end, and I'll just briefly talk about these. So there is clearly some kind of close connection between the construction that I just gave and maybe frequentist inference more generally and possibility theory. So I actually was sort of relatively recently kind of had some inspiration. Actually, I heard a presentation by Dominic, who I think is still here, talking about possibility measures over the summer. And I don't really know why, but things sort of clicked in, and I realized there was maybe another way to formulate this inferential model construction sort of directly using these possibility measures. So this was a relatively recent paper about that. I think that maybe there's this question that I kind of left open was about the optimality. So the questions about the what's like a best sort of random set for such an a particular problem. I don't know that this necessarily solves it, but I probably need to dig into it more. There are I've seen in some papers, Dubois and maybe some others talking about what are kind of the best or sort of tightest possibility measures as kind of bound, basically they're kind of bounding something, and then what are the tightest bounds. There does seem to be some connection between those type of results and what would make a sort of quote optimal inferential model. And then there are some differences, I think, in terms of these constructions, but maybe in certain cases there's some equivalence. So I think that would be of some interest. There was one technical point which I didn't even mention as we were going, but it is possible for this thing to be empty. So you could have some realization of this guy actually end up being an empty set. This is a problematic case, and there's a couple of ways to deal with it. One is you can condition out those empty cases. That's essentially what the Dempster rule would do. Another thing, which actually my colleagues had originally done this, was talking about stretching the set. So I won't get into that, but the stretching is actually an alternative to a Dempster type of conditioning, and usually gives some results that are more efficient than had you use the Dempster rule to eliminate these kind of problematic cases. So I'll not say anything about that specifically, but if you're interested, you can find this was in an IJAR publication a few years back. Okay, question here from Dominic. The empty cases correspond to subnormal possibility distributions. Yes, so if there's some cases like where it might be empty, then like if you think about the possibility contour, like so it's like where the random set contains a particular point. So if there's some possibility for the random set to be empty, I mean, right, it's like what makes it go to one is that if they're nested, there's going to be some point that's contained in every one of them. But if there's a possibility to be empty in some cases, then that's going to drop down this possibility contour may not reach one, because those empty cases are ones that they're going to occupy some probability, and they're not going to be ones where this particular parameter value is in there every time. So that'll drop down the peak. And so then it'll be less than one. And so the conditioning is essentially where you just condition on that they're non-empty, that bumps it up to one basically by dividing, renormalizing. If you do the stretching, it's kind of to avoid doing the global normalization, right? So if you divide out if you condition on the non-empty case, you're just across the board dividing by something less than one, which will boost this plausibility contour up. And so higher plausibility contour reduces efficiency. It sort of makes the thing just overall bigger. There's other ways to force it to go up to one, and that's what the stretching does. Share some code to play with the method, the reduced. So the conjunction model, you mean the satellite problem? Is that, Dominic? Let me look. So I must have it, but I need to find it and probably need to look and see if it's readable. But yeah, I'd be happy to share some things with you. Yeah. Maybe if you send email, I might forget if you don't remind me. So if you can send me email, I'll look for it and find for you. Okay, so that's the end of my part two. I guess if there's other questions, I'm happy to answer. Otherwise, we can move on. Okay. Okay, Dominic has another question. Subnormality. So, okay, so where this, where where these empty cases can come from, it's usually not where, well, typically where it comes from is that there's constraints. So there was at one point earlier today, I mentioned that in the, in Fisher's original formulation, he was assuming that as you vary the parameter, so like imagine the CDF f theta y, and as you vary the parameter, it can go everywhere 0 to 1. So if that's not the case, so like it may be possible actually that if you fix the y and then you vary theta over the entire space, it doesn't span the whole 0, 1. So what can happen is that in a case like this, which can show up sometimes unexpectedly. So actually in this, I mentioned it here, but then told you I didn't want to talk about it, is so there's some constraints that appear coming out of this non-central chi-square distribution. So that's one where there's some, it doesn't necessarily span the whole thing. Like if you look at the CDF at a fixed y and vary this phi over all 0 to infinity, it won't span the whole 0, 1 interval. So then you have to do, then this can create some opportunities for the random sets to be empty. And then you try to correct for those things. So it's not that I somehow made bad choices. It's that there's certain problems that can have these constraints, and then you have to do something to correct for them, like to basically to ensure that things are valid and efficient. You have to do some correction. These are normally not significant corrections, but it's kind of too technical to describe here. It sounds like, Dominic, you're talking about maybe a very different situation where it's kind of like, well, I guess I don't fully understand, but it seems like maybe this is coming from something more, a more structural issue inside of your application. So I don't really know. So yeah, I'd be happy to, since I don't really know what you're talking about, maybe it's best to, we could talk afterwards or something. Okay, I think that was all I wanted to say in part 2. So part 3 is, well, relatively short and not really technical. But what I wanted to do was to, I wanted to kind of say a few things about, I guess, things that I think are interesting and worth looking at, things I don't have really the answer to. Part of this is that, I mean, it doesn't really help, I guess. I mean, well, one of my goals is that, you know, after these things, you kind of know something about what I'm talking about. And that if you're interested, you might have sort of now the background to kind of start digging into things. It's hard to like pick up a book and like learn something and then do something. So I was sort of hoping that my explanation of some of these things, which I, you know, when you're writing a book or papers or things, you try to say things more formally, but at least if here I can talk more intuition, and hopefully that actually makes reading the books and papers easier. But any case, so what I was hoping was that this would kind of, if you're interested, this would lead into some projects. And so it's hard also to come up with your own projects if this is a new area. So I thought it makes sense for me to say a few words about things that I think are interesting and haven't been solved. And then, you know, if you wanted to talk some more about it, or you wanted to take off and do it yourself, that's all great. So that's what I wanted to do in this sort of third part. So very few details. It's more just kind of like thoughts. So the few things I wanted to mention, one is about efficiency and optimality. So I had some discussion with Jasper in during the break, kind of related to these kind of questions. There's another issue, which I think is one where having this connection to imprecise probability is actually very helpful, is situations where you know something about the parameters, but not enough to really say, here's a prior distribution that I want to use. A few remarks kind of about this false confidence phenomenon, and maybe what's going on there, what's the structure that's causing this, etc. Various ways we might try to modify or weaken that validity condition. And then basically, I mean, it's that computation is a challenge, and I hope that maybe you guys know how to solve something like that. So the first thing is kind of is here about efficiency and optimality. So I described those dimension reduction steps before. So let's suppose that we've done all of those things and we're to the point where we can't reduce anymore. So then now I'm just going to call that reduced auxiliary variable u. and there's some distribution that it has that I know. And so the question is, how do I guess or predict that thing with random set? So then this comes down to how do I pick what's the best random set? So we have some optimality results, but I think these are not, these are definitely not conclusive. Basically what those things are focused on is that if there's one assertion you care about, how do you design a good random set that will make sort of most efficient inference with respect to that assertion? So it's not fully satisfactory because, if you had only one assertion that you were interested in, then you maybe wouldn't bother with constructing a whole inferential model for this, to be able to do uncertainty quantification about any kind of assertion. Right, so it's not fully satisfactory that you kind of need to construct this whole machine and then focus it on this one particular assertion to define optimality. But I guess an interesting question that actually, while I was writing this, I thought of was that, suppose we could do this construction and say for some or maybe all assertions, I knew how to construct the optimal random set, sort of the best one. So would it be possible to do this fusion like I was describing earlier? So basically to have optimal random sets corresponding to every assertion and then do the fusion in the way I kind of described earlier. And that in some way, this would lead to something which is kind of like the best inferential model. I don't know if that even makes sense, but that was something I thought of. You could also say, well, maybe I don't want to go for a single assertion. Is there some sense in which we could say a random set is kind of overall good or overall best? And what maybe would that look like? I don't really know. So one thing, I guess, maybe to give some perspective. So it is actually possible to rewrite this whole thing. So in the following sense, that I don't necessarily have to work out what is the optimal random set, the whole thing. So there is actually a way to describe what kind of condition this random set distribution needs to satisfy in order for validity to hold. And so it looks like this thing here in the middle. I don't know if that's all that helpful to stare at. But what this ultimately does is it says that if you can tell me what the collection of the focal elements should be, so this is basically like the support of the random set. And so here, these are assumed to be nested. So if you can tell me the support, like the sets on which it's supported, then this is how you can allocate this is how you can define that PS distribution through this kind of requirement. So what this is doing is just looking at all of those sets in the support that are contained in some generic set K, and then I maximize. So this obviously requires the support sets to be measurable with respect to this P of U distribution. But anyway, so then this would be a way that you can assign the probabilities and define this P of S, but that requires first knowing the support. So now this question about optimality and efficiency really comes down to, or it can be rephrased in terms of picking what is a good support. And this is how I thought maybe this was related to the things about possibility measures and the type of properties that are known there. Is, I guess, my conjecture about whatever would be sort of the best support is that you imagine it's kind of an index, let's say tau. And so then you would define like the S of tau as like level sets of the density function corresponding to this P of U distribution. So whether there's density functions maybe I mean, that's a separate question. But if you do have a density function for this P of U distribution with respect to whatever measure is there, say Lebesgue measure, then this would be a way to define what is sort of the quote best support. This seemed to be confirmed by some of the things I was looking at over the summer related to possibility theory that's in this paper. So I don't know how far this goes and exactly what the conclusions are, but I think that there's something to be said about this. Intuitively, this makes perfect sense. I thought of this well before I knew anything about possibility theory, but then I saw there was this kind of connection with possibility theory and thought that that was further reason to think that this is probably correct. I think the question then is just, what does best mean? This seems like a very natural candidate for whatever best is, but then I don't know what best means. So that really is the kind of the main question. How do you define best in such a way that this would be the thing that is best? So now I would shift so that, yeah, these are just kind of like quick things about random thoughts about these questions. So then jumping next to this issue about the partial prior information. So at least in the statistics world, it's kind of interesting, this kind of polarization is that there's basically two possibilities. One is that you know everything about you have complete prior information and you can directly write down prior distribution for the thing that you're interested in. And then from there, it's very natural you go in the Bayesian route. The other side is that, well, suppose you have no prior information. And then there you normally follow in kind of this sort of quote frequentist approach. And that was the context that I was thinking about in parts 1 and part 2, no prior information. But these are two extremes. And so probably every problem in some sense is in between these. So then what would you do, right? So here's an example that I've actually worked a lot on, not specifically in this context, but to just sort of general interest in high dimensional inference problems. It may be that you have information that says that this high dimensional parameter has some low dimensional structure. So a common type of low dimensional structure is sparsity. So sparsity here just means that, imagine that my parameter is very high dimensional, it's a big vector. So the low dimensional structure might say that, well, many of those entries in this big vector are 0. I don't know where they are or how many there are, but most of them are 0. So something like this would be relevant, for example, if you're thinking in a regression problem, maybe where I have thousands of predictor variables. So imagine like the linear model sort of layout, you have a y equals x beta plus error, and the x is a really wide matrix. So then you have so many of these predictor or explanatory variables, and there's just, maybe the science says that, well, we measured all these variables, but probably not all of them are important. So an example is like if maybe these are related to some kind of like in a biology type of situation where maybe you're measuring lots of things related to all of the genes on the genome, and these are like your predictor variables, and you're interested in how do these some features of these genes influence traits. So they have some biological theory that would say, well, traits aren't influenced by tons of genes, they're only influenced by a few genes. And so we're trying to figure out what are those influential genes. So if you think about this in a regression problem, you have this coefficient vector that's getting multiplied by these different variables. And so if I want to sort of incorporate into my analysis that the biological assumption that most of these variables are not important for explaining variation in this response, what I might do is say, well, I think this high dimensional beta is actually sparse, has lots of zeros in it. And so then I want my analysis to somehow incorporate that, that structure, that assumed structure. So the reason why this is somewhat problematic is that, well, you kind of only have partial information because the information that's real is information about sparsity. But then if you wanted to be in this like first case, complete prior information, you have to make up prior information about the structure specific parameters, like the values of the beta coefficients that are not 0. Right? And that's all made up, right? So that's not real prior information, that's just made up for convenience. So what we'd like to be able to do is to incorporate the prior information that's real and not require prior information that you don't have. So I think that the imprecise probability framework can actually help with this. It's that you can essentially write down a partial prior distribution, which is basically described by a random set or one of these other kinds of objects about that parameter of interest. So this incorporates the structural assumptions, but doesn't require any other side information. So then what you can do is things like, okay, I have an inferential model coming from the data, I have inferential model coming from the, maybe I shouldn't call it inferential model, but I have some random set or some kind of an imprecise probability model that describes the prior information about this parameter, and I want to combine them in some way. So a Dempster rule or some other kinds of things like this. All right, so that's, I think, is a very reasonable strategy here. Something that's sort of problematic about this is that these kind of typical rules, like a Dempster's rule or other kind of combination rules, these aren't designed to preserve validity. So even if I start with a inferential model that's valid and then I combine it with some reasonable prior information, this is going to ruin the validity property. So maybe that's worth it, right? Because you're incorporating this real prior information. So if that somehow ruins the validity property, maybe that's just the price you pay. but that leads to some kind of a question. Is it possible actually to incorporate this prior information in such a way that you improve the efficiency because you're somehow, you kind of, what's the right word? You're kind of forcing the structure in. So then if that structure is real and you force it in, then somehow you're going to do better than if you didn't force it in. So that's this kind of improved efficiency sort of notion, but without ruining the validity property. So yeah, last year's SIPTA, Leo and I had a paper about a very basic kind of problem, but kind of trying to think about how you could bring in this incomplete prior information that will improve efficiency, but not ruin validity. So we're working now on how to kind of deal with this high dimensional structured like sparsity problem. But this is, of course, is hard. And so still looking for an answer to that. So the next thing was about the false confidence phenomenon. So I forget who it was, but there was a question yesterday kind of asking about what's kind of causing the false confidence. And I don't really have an answer to that, but there were some thoughts, and I mentioned these yesterday, so I can say them again. Of course, it's fine. So remember, the false confidence theorem, what this result was saying was that if the inferential model has a additive output, so this is like a probability measure as the output, then there will be false assertions that tend to be assigned high belief. So what's going on here? So I mean, I guess the statistician's feedback on this is that this only happens for trivial assertions. So definitely there are trivial assertions for which this happens, but our argument has been they're not only trivial assertions. It doesn't seem to affect they don't seem to recognize that. But in any case, so then you can ask, okay, how serious is this really? Like, so is it really that there's only these trivial kind of assertions for which this happens? And so basically to answer this, you'd have to try to say, well, what are those problematic assertions? Can we somehow characterize them? Can we say what basically is causing the false confidence? Like I mentioned yesterday, that based on my experience at least, where these things are coming up is that when you're dealing with some kind of a interest parameter, and that's a nonlinear function of the full parameter. So the two cases that we looked at where I've actually shown you these problems was that satellite collision where the interest parameter was the norm, so a nonlinear function of theta. And the other one was this Feller-Creasy problem where the interest was the ratio. And so this, again, another nonlinear function. So there's other literature, I mentioned this yesterday, about sort of describing challenges that are related to nonlinear marginalization. So this Glesser-Huang paper gives, sort of shows actually that there's certain cases where there's a non-existence result that says that there are no bounded confidence intervals with positive coverage probability. So actually a very extreme kind of issues related to this nonlinearity. And Don Fraser has a paper from 2011 about how the nonlinearity can affect the Bayesian solutions to these problems. So I don't really know whether this actually helps. It seems, I mean, it's like there's some intuition about what's going on, but it's hard to kind of write down mathematically what might really be the issue. This nonlinearity seems to be, it's at least like the best clue I have right now, but obviously would be open if there was other thoughts, and if you knew how to solve it, I'd of course be excited to see that. So then this was something that's come up more recently that I've been thinking about, is like the validity condition that was specified is actually quite strong. And so there's a couple of ways in which it's strong. One is that I'm asking for this to hold for every assertion. And then the other one is that I'm asking for that property to hold for every alpha. So I guess a couple things to say here about each of those potential relaxations. So one that you could do is you could imagine, so instead of requiring it for every assertion, how about you identify some class of assertions, some proper subset of the power set, and then require this to hold for all of those assertions in that subcollection. So this, basically what you could do is you could say, if I knew what were the bad, sorry, if I knew what were those problematic assertions on the previous page, like related to false confidence, then I could prune those out and then say, well, a inferential model that has additive output would be valid with respect to this subcollection, right? So this would somehow give us a way to sort of understand what you're giving up. What are you giving up by requiring, we have to give up, in order to be valid, right, we need to have some imprecision. That was one of the things that were shown. But if you relax what it means to be valid, then you can get closer to, I guess, getting rid of this imprecision and sort of understanding what's the trade-off is that if I want to be valid for this bigger collection of assertions, then I need, this much imprecision. So this would help, I think, to understand kind of what's the trade-off between, the amount of imprecision that's added versus the sort of the scope of validity. Okay, so I don't think it would be interesting to say, take this subcollection as just a few things, right? We're trying to do uncertainty quantification in a reliable way. So it needs to be a big collection, but it may not need to be all the assertions. That maybe is too much. And so you could sort of ask, what can we gain on one hand by relaxing this and only requiring it for some relatively large subclass of assertions? And the other thing is about this alpha. So this seems to not really matter all that much. Like if you said, okay, let's change this. If I didn't require it to be for all alpha between 0 and 1, how could that really affect things? So actually not so long ago, I found this paper of Peter Wally's JSPI 2002. So what he's working on there is a situation where he's using like a generalized Bayes sort of formulation. And so there he's got starts with some kind of like collection of prior distributions. And so you start with this collection of prior distributions and you can update to a kind of a generalized posterior using this Bayes rule that he describes in the book. And so this leads to he's able to get a lower probability, let's say, on the parameter space. So exactly the same kind of context here. And he's able to say that if you only require this validity condition for alpha in some 0 to alpha bar, and alpha bar is strictly less than 1, that then you can achieve exactly the validity property, but on this restricted range of alpha using the generalized Bayes. So there's a flip side to it, is that the generalized Bayes is actually quite inefficient. So he's able to achieve validity, but not in an efficient way. But it still is interesting that just by adjusting the range where you require this alpha to be, that creates some new opportunities. So using just kind of this basic generalized Bayes framework can actually be valid if you restrict this range of alpha. And so the question really is about how can you balance this? So his construction is not very efficient, and so you'd like to do better. And so is there a way to kind of incorporate his ideas with the ideas here to try to do a bit better? So Mateus has a question here. Okay, so Mateus is asking about the whether the threshold, I guess this alpha threshold, could depend on the assertion. So just to make sure to clarify. So jump back to the definition. Here. So just to clarify, Mateus, so you mean this alpha or like this one here? Inside or outside? Outside. I think like, so mathematically that seems fine. I think on the inside, I maybe wouldn't want to do that. So the reason I wouldn't want to do that is that you ultimately are going to want to make some, you're going to try to interpret this and you're going to say, okay, well, I'm going to compare my lower probability or upper probability to this kind of cutoff. And so then it doesn't really make sense that the cutoff would depend on the assertion that you're actually considering. So, but whether it could depend on, whether this guy here could depend on, this one could depend on assertion. I mean, I think mathematically there should be no problem with that. Whether that, I guess interpretation wise, what does that do? So, I mean, I guess this condition only really carries some weight if when the threshold inside of here is big, that the number over here is small. So I think that I mean, it can maybe it could depend on the A, but not in a very like strong way. It would be sort of like a weak type of dependence. So like if this was almost like monotone in A, I think maybe that would make sense. I see Scott says he hates that idea. I think mathematically it can work, but I don't know interpretation wise. I think that's difficult. I guess I tend to agree with Scott. Sorry, Matthias. Let's see. All right, so I'm very interested to dig some more into this, into Wally's paper, because I think that this, I mean, right now what's happening is that seems validity only really matches up with possibility theory. And what Wally's constructed is not a possibility measure, but yet it still can essentially achieve this validity condition if you relax the alpha requirement here. There's also a loss of efficiency. So I think that it's interesting to kind of see this interplay, is that you can be maybe valid and efficient using possibility theory, but if you want to go to something more general, like what Wally constructs here, it seems that you pay some price in terms of the efficiency. So I guess towards this weakening the validity condition, I was thinking recently, actually this was in that context of prediction that I was working on with student Leo. So in this context, what we were interested to do is that I can observe a y and I want to predict, let's say, a y tilde. So y tilde maybe is like the next observation in the sequence, let's say. So what we were thinking about there was, I mean, so validity is harder to describe in the prediction problem because there's no such thing as like true and false assertions, because what you're trying to do is you're predicting something. So if I set some assertion A, then the next thing y tilde could be in there or not. So it's not certain that like this A is going to be true and this other A is going to be not true. So you can't think of it as like that we only assign that we only assign or that we don't assign large beliefs to false assertions. That doesn't make sense in prediction context because there's no notion of true and false assertions. That's kind of like just, yeah, that just doesn't exist. So we were thinking about a sort of different definition of validity in that context. And so what I've written here in the actual expression is a bit messy, but underneath it, I think is the one that's easier to interpret. It says, so here I'm thinking in terms of the upper probabilities. But what I would require is that this sort of joint event that I assign a low upper probability to an assertion A and the y tilde is in A. So it's like this joint event, of course, can be true or false, right? Because it's, I mean, that's an event, it would happen or it wouldn't. And so what you can say here is that it would be a bad situation in the sense I'd be making a mistake if I assigned a small lower probability to an assertion that happened to be true. So this is kind of a relaxation of what we had been talking about previously. I mean, the relaxation is just that now I've introduced this extra thing, which is the y tilde in A. So this helps me deal with the fact that there's no A that's like absolutely true or absolutely false, but I can insert this other sort of make it a joint event between two things. And now inside of here, this is like, this joint event would be a case that's bad in the sense I might be making erroneous predictions. So then what I try to do is I would insist that this joint event has probability that's not too large. Okay. Now, the reason I wrote this other thing is that it actually, I think there's some interesting things to see in this other formula. So all this is doing is like you write this probability and then you expand it as like the expectation of conditional probability. And if you do that, then things kind of simplify. And so what you have here is it's an expectation of a product of two things. One is an indicator that the lower probability is smaller than this alpha. And the other one is this conditional probability that y tilde is in A. Okay, so now what I want is for this to be less than alpha. And so what you could see from this one is that if I would define this upper probability to be the Bayes rule when the distribution is known. So like if I know the whole distribution, then I could actually define this upper probability to be equal to this thing. Right? And if I define that to be equal to that, then I can easily satisfy this condition. So this is the sense in which a Bayes rule would be valid. If we take this as a definition of validity, then Bayes would be valid. But you see that you have to know the distribution in order to achieve it. Right? If you don't know the distribution, then Bayes being valid is that bets are off. Another thing is that if I suppose I have a set of candidate models, and I could do a generalized Bayes rule to get a corresponding the upper envelope for this credo set, right? So if I do like that, and if it happens that the true distribution is in the set, then I get the same story, because this one would be the maximum of all those things. This one would be one of those that's in the collection, and therefore, if the maximum is less than alpha, then the whole thing is less than alpha. So I can achieve this kind of validity with Bayes or with generalized Bayes, but it assumes some knowledge about the true distribution. Like, so either I know it, or I have a set of candidate models that I know it contains that. Something else that showed up in these considerations was that it's actually, you can check that in this particular context, the validity would imply the no sure laws. So seems like there's some connection here between this validity condition and some of these other more familiar kind of, at least these other conditions that are more familiar to the imprecise probability community. So I thought that this was a sort of a curious observation. I mean, intuitively, right, if something like using something because it's valid, I mean, that if it doesn't really make sense, like internally, it's kind of hard to say, well, I'll use it because it's valid. So there must be some connection really between this kind of notion about valid inferences or valid predictions and, actually satisfying these coherence properties, right? So like there has to be some connection between these things. I mean, how I've presented it so far is that the validity is kind of an external, basically a calibration type of property, whereas coherence is kind of internal. It's like an internal consistency. And it doesn't seem like those things should be separate, right? That you could use something that's internally inconsistent, but still performs well, or that you could use something that performs well and not be internally consistent, right? That somehow that those two extremes don't really seem right. So anyways, it seems as if there should be some connection. I was excited to see that this is at least one such connection. So this is in the context of prediction. Question would be how to extend this kind of framework, essentially a version of this kind of condition, but now in the case for inference. Thinking about, you might have some prior information, and that would define sort of like a posterior distribution for parameter given data. And so if there's some notion like that that's sitting there, you may be able to justify a definition like this in an inference problem and then see where it goes. So I don't actually know where it goes. And maybe I think one of the last things I was going to say here is about computations. So it's obviously what we're doing here is to try to create something that has some practical value, and so it's fine to develop the fancy kind of random set type of stuff. But if we don't know how to compute these things, it's hard for this to ever really make some impact in like real world stuff. So it's essential, imperative that we be able to compute this stuff. So what I've shown you here, in most of these cases, the computations are not so difficult. And so you can do them. You can, I think there was probably not any of the examples I showed you, but I think we've had some examples where maybe we had to do some MCMC type of calculations, but not involving anything like imprecise probabilities. So I think it would be of some interest if you kind of get beyond these kind of textbook problems. And I know that your group has done lots of things like this, but I don't really know. That's something I don't know anything about. So you might actually know how to do these computations. So I mean, I guess to make some analogy, I guess I don't know if you're familiar with these things. So I mean, back in like the 1980s, let's say, basically nobody was Bayesian. Nobody did Bayesian things because you only knew how to compute posterior distributions for relatively simple problems. But it was sort of this kind of simultaneously like computational, both the algorithms and the machines became more powerful. And so then it became possible to do Bayesian computations in some non-trivial problems. So this all really had something to do with like development of Monte Carlo methods and MCMC type of methods. There's nothing really stopping, I mean, you can do exactly the same things if you're talking about random sets and computing these lower and upper probabilities, but obviously the machinery is much more technical because, I mean, it would be ideal if you could just say, here is my random set distribution. Like I tell a function in R or Python or something, here is my random set distribution, and just tell it to crank out, just simulate these random sets, plug them into the thing, and you could compute the lower and upper probabilities immediately. That's maybe too high up on a wish list to be achievable. But if such a thing existed, then this would be, you could just create these kind of black box type of functions that somebody could use and just say, just hit run, and it will generate these realizations of random sets and compute these lower and upper probabilities for inferences. That maybe isn't possible, but I mean, that's, I guess, something that would be really nice. I guess similarly, if we're focused sort of specifically on this kind of case with nested random sets, then there's this optimization that needs to be solved. Optimization problems are maybe a bit more tractable in the sense that you don't directly have to deal with the random sets, it's just optimization. But if there was, I mean, when you get into higher dimensions and things, obviously this is not straightforward. And so this isn't specifically a problem for imprecise probability, but I guess if you've been calculating these possibility measures for years and years, you might have some good strategies about how to solve this. You want these things, I guess, to be simple solutions. I think that people tend to have higher expectations than they should about how simple something should be. So obviously we want it to be as simple as possible, but I think my expectation isn't that you'd be able to do these computations in an instant. It may be hard to do these computations, it takes some time, but at least knowing how to do it in an efficient way would be really, really valuable to me, and I think to others. So the last thing is, I guess, not really like sort of side note. I mean, this is something I've been kind of thinking about recently, is that this seems to be, I mean, maybe this is being too bold, but I mean, it seems as if this connection between imprecise probability and how it fits into statistical inference, not necessarily because models are imprecise, but because the imprecision is sort of necessary for this kind of reliable uncertainty quantification. This seems to be new, and I think, I mean, it feels to me as if this is would be a really nice opportunity. Really, this problem in statistics is completely unsolved. So, I mean, we don't really know what to do if there's not prior information. So it's really just kind of ad hoc. We can come up with different methods and different procedures. And if you look at an issue of any stat journal, there's 20 articles there, and they're all proposing to do something in the best way. Right? It's like there's really no sort of systematic type of way of dealing with these things, and especially from frequentist point of view, it's just whatever seems to work is what we do, and there's not really like a fundamental understanding in my view of sort of what's going on. And I think that imprecise probability does create that opportunity, because if we understand that what a frequentist really wants to do is to have this type of a valid inferential model that's maybe through possibility theory, then that provides some kind of framework, and then we can, maybe make some more sense out of what it is that we're actually doing. I think on the one, this is something that really can't happen in the statistics community, unfortunately. There's maybe lots of barriers that I think will prevent this. And so, I mean, part of this is my own opinion, but I think that this is actually true, is that there's really no opportunity for foundational work in statistics. It's not something that's people are going to have success with, and so they're not going to do it. And so regardless of whether these are good ideas or not, it's just not going to happen. But I think that my limited experience with this group is that very open-minded and actually, want to solve interesting problems. And so that's why it was really great to have this opportunity to talk to you guys and actually to say what all this stuff is. I wouldn't expect that you would go and dig the things out and figure it out yourself. So it's great for me to get a chance to come and talk about it. So I guess really the end thing for me is that, if any of you are interested in doing these things, and let's do it. So then finally, you can find papers of mine on my website. I guess at some point these videos will be available. I guess you can watch them. Regardless of whether they're available somewhere else, I'll try to curate them in my own place so that they can easily be found. But definitely, if you want to talk to me more, happy to email exchanges or whatever. And so also one last advertisement, and check out the Researchers One website. The new conference is coming actually next week. Our first virtual conference is coming next week, and then some other things we're hoping to push out relatively soon. So yeah, thanks for letting me talk, and I guess and for listening. So thank you.
Thank you very much. Let's give a round of applause.
Thank you.
I sound from me only, but I guess everyone's muted. Thank you very much, Ryan. It was fantastic. I really enjoyed it. Well, we have time for questions and informal chats, so I think we can stay on the call for a bit.
So Dominic asks, I guess I don't, maybe not a question here, but about, I guess, okay, so it's about the ability type of stuff, but I wanted to focus just on p-values. So p-values are things that students learn, but then they kind of just get this one particular role, is that they are used in hypothesis testing, and then maybe even they're not good for that because everybody wants to ban them.
You still needed to be a little radical by invoking p-values, right?
Yeah. So what I was doing here was I tried to kind of outline how you might teach such a course. I've not actually done it myself, partly because the course was never the right one. But the basic idea was that you could sort of treat these p-values in this way, and that you can, the way you would do kind of like to aggregate over different values would be to maximize, and that it inherits these kind of nice properties. And sort of focusing on the first examples here about normal and uniform, you can draw some plots to kind of visualize, get into some kind of more complicated example. I don't remember what's like the most complicated thing I showed here, but I think that normal example where you might try to first draw the joint thing and then do the marginalization, that makes sense. There's actually another way to do this I didn't talk about in the presentation today, but another way to do this kind of dealing with the nuisance parameters would be, this is at least in this context, kind of using the, not using the association as I described, but kind of a generalized one. You can actually do the marginalization kind of in the statistic itself. So by doing something like a profile likelihood ratio. So then this thing only directly depends on the thing of interest. So this function here only depends on the interest parameter, not on the nuisance. But its distribution still depends on the nuisance parameter. So then you have to deal with either some asymptotic approximations or doing like a, I guess somewhere I must have something about Monte Carlo, but yeah, here, I guess here's one kind of example where you can see like this sort of joint plausibility contour there. So anyways, I did try to write this paper as if like I was explaining how I would teach this to undergraduates, or maybe like a master's level type
So
of.
it might be the backbone of such an introduction then.
Yeah. Yeah.
Okay. And you mentioned the absence of software. Do you think that, I mean, there's some expertise in software development around here. Do you think would be profitable to try to do some of those things, or is it premature, do you think, or post-mature?
Profitable, like in terms of money, or?
No, but conquering the world.
Yeah. I think that there is something to that. That alone isn't going to, I guess, to create, make a revolution possible. But there's always going to be some without it. The only obstacle is that they don't know how to do it. And so then if those tools were available, then they'd have no excuse, basically. So I do think that that's the case. And, I remember Michael was talking about this, about that particular satellite problem, about developing some software to actually do the thing that we suggested to do. I don't know what the status of that is. But yeah, I think definitely to actually show that these things can be, that you can actually make practical solutions out of this that are good, and there's software to actually make it work, and that it's a real thing. It's not just I think in at least in statistics, there's kind of this impression that the imprecision is just sort of like it's not something that you really need, that it's like a technical thing that you would add on to kind of make something seem fancier, or it's just that you could handle it in other ways. But I don't think that that's really true. So, to show actually the benefit of these things, we need like practical solutions for the real problems. And that I guess requires software.
Yeah, there were no Bayesians before WinBugs, were there?
Well,
maybe there were two.
Yeah.